behalf of Dr. Sriram Sharma, the chairman of the Solnet, Dr. Sri will join us very soon for giving you a good welcome. In the meantime, let me welcome all of you to this exciting event today, which marks the 2 years of very active period of Solnet. The South Asian Lightning Networks has been found in 2019 September. So we have already worked for 2 years in the region with the support of many international experts as well as regional experts. And so it's a story of success. And as Dr. Sriram is with us now, I would like to invite Dr. Sriram, the chairman of SALNet, to deliver the welcome address. Dr. Sri, over to you. Dr. Sri, are you there? Okay, so if Dr. Sri is not able to join us, yeah, Dr. Sri, please.
Yeah, thank you so much. Thank you so much. To deliver a kind of welcome note or welcome to all. I can see Professor Marian, I can see Professor Colin Price and all my invited. I'm unable to see Mitch yet, but I would like to welcome all the invited and panelist speakers today for this very nice event that we are going to mark the foundation day of South Asian Lightning Network that has already grown by 2 years now. And I'm very happy to have you all in this. Most of the experts who have been contributing for the development and progress of South Asian Lightning Network are way. I'm so happy, so glad to have you with us. And you know, this is a very for us very memorable moment that we met together in Tripura 2 years back, and we are celebrating this event today, though virtually. We thought of a meeting physically, but due to ongoing pandemic, we could not do it. And this was we were planning to meet in Nepal, but unfortunately this could not happen. But still, we could mark it the South Asian Lightning Networks Foundation Day. And I would like to first of all welcome both the invited speakers, Professor Colin Price and Mr. Mitchell, to have today with us to deliver a very interesting talks on very interesting 2 events or 2 phenomenon associated with lightning. One is on lightning and the climate change of future of lightning, and the other one is technical perspective of lightning protection system. So I am very glad to have both of them today in the program, and of course all the steering friends from around, Professor Marian, Professor Chandima, Professor, you know, friends panelists from all around. Professor Ajit Tyagi, I guess he's around. I can't see though, but he might be there. And all the respected panelists, Professor Jainal from Malaysia, and all the respected panelists, I would like to welcome you all for the event. And through these 2 years, what we have done is most of the time we have done the online or virtual programs. Okay, Professor Tyagi, you are here. We are joined together from different entities, South Asian Meteorological Association, and from ADPC, I guess Mr. Man Thapa is there from Nepal, and from RHIMES, Dr. from RHIMES, I think we have the friends from around. So this is a kind of a celebration among with the networks and institutions, different institutions from around. So this is the time where we start our, collaborative action or efforts with the partners around and institutions working in the field of lightning meteorology and so on. So why saying? Because all are waiting, desperately waiting for the invited talks and panelists' views on these things. So I would like to request Chandima to carry on with the invitation and speeches. And again, I would like to welcome all the panelists, invited speakers, and participants from around to this very wonderful event. Professor Chandima, it's over to you. Thank you so much.
Thank you very much, Dr. Sriram, the chairman of SALNet. We'll go straight away into the presentations today. So we mark this event with two concurrent topics presented by two of the eminent speakers in the field of lightning. And the first presentation will be on lightning and thunderstorms in the future climate. So we are going to hear about what these global climate change and what we hear every day about a changing climate in the world is going to affect the total scenario of lightning and thunderstorms, and finally, what would be its impact on the general public. The presentation will be delivered by the eminent professor Colin Price. Colin is a professor in the Porter School of the Environment and Earth Sciences at Tel Aviv University, Israel, and the head of the Department of Environmental Studies. He is a well-known atmospheric physicist specializing in the Earth's weather and climate, with a focus on thunderstorms, climate change, and natural hazards. He was born in Johannesburg, South Africa, where I am at this very moment, in 1962. After starting his university studies in South Africa, he transferred to Tel Aviv University in 1982, where he completed his BSc and MSc degrees in geophysics and atmospheric sciences. He received his PhD at Columbia University, New York in 1993, while working at NASA's Goddard Institute for Space Studies in New York. After completing a postdoctoral fellowship at the Lawrence Livermore National Laboratory in California, he returned to Israel and joined the faculty of Tel Aviv University in 1995. Colin has published more than 150 scientific papers and has a team of 15 graduate students and researchers working under his guidance on various scientific research projects. So, Prof. Colin Price, the podium is yours. Please.
Thank you very much, Chandima. Can you see my screen?
Not yet. Yes, of course we can.
Please there.
Yes.
Please there.
You're good. So thank you, Shri, for the welcome, and thank you, Chandima, for the introduction. I'm very happy to be here, and I have fond memories of 2 years ago us meeting in Tripura and starting this network. So I'm very happy to be here today and to share some of my research and thoughts about lightning and thunderstorms in a changing climate. Well, we all know that there's been a lot of press coverage of the latest IPCC report about the climate, the state of the art of the climate, and I think it's fairly clear to us now that the climate is changing, the globe is getting warmer, and this is impacting on severe weather, extreme weather. And we all know that lightning is a major cause of death, injury, property damage, and also forest fires, mainly in high latitudes. And in the tropical countries, and related to this network, mainly rural communities are the most vulnerable to lightning, especially farmers and people working outdoors. And we don't have that much data about changes in lightning in the past. Our global networks have not been around for more than a decade or so, and most of them are incomplete. So we don't really know what's happened in the past. So I'll show you some evidence of changes in lightning and thunderstorms looking backwards in time. But the question is, what can we expect also in the future? As you can see on the map below, the tropics are where we have most of the lightning. Maybe 90% of the lightning on the planet is in the tropical regions.
Sorry to interrupt. Sorry to interrupt. I think the slides are not moving.
Can you see the one with the map at the bottom, the motivation?
No, we are seeing the first slide. And it's not in full screen.
Well, I only went, let's see. Stop sharing and I'll try to do it again then. Share screen. Let me try. Just a second.
You can share the screen instead of window.
Yeah, do you see it now? The first slide?
No, we are seeing the all your files.
And now?
No.
I see it on my screen. I don't see. I'm not sure what I'm doing wrong here with the sharing.
Probably you can share the window, only the file.
Let me open this up as it was before. Okay, let's stop sharing. Sorry about that. The window.
Yes, perfect.
You see it now?
You can see. Yeah.
And you see
the first slide. Slide
can you see
number
this?
1.
And do you see me changing the slides?
No, unfortunately.
Maybe it's in the full screen mode. Do you see me change now?
Yes, now we can see the second slide, motivation, surface temperature and lightning. Yes, now it goes.
Okay. So I think the full screen mode for some reason doesn't work. So I'll leave it in this mode. So as I was saying, basically most of the lightning is in the tropics, as you can see on this map at the bottom, which is from the satellite data from the LIS, the lightning imaging sensor. And so there's a lot of interest now with climate change of how thunderstorms and lightning have changed and how much they will change in the future. Now, when we talk about climate change, everyone normally talks about temperature only, the global warming, global temperatures going up. And so there've been lots of studies looking at the link between temperature and lightning activity. And generally, the vast majority, I think there's only one study which doesn't agree with the others, but most of them, 95% of them, show a positive correlation, implying that as things get warmer, we have more thunderstorms and more lightning. Whether this is on a daily basis, the temperature during the day, if we're looking at a seasonal cycle or El Nino, or climate change and using models. And so it appears that it's fairly likely that we can expect to see more thunderstorms and more lightning as the temperatures increase. And here's one example that we studied over Africa for just a 2-3 month period in 1998. The black curve on the top and the blue curve below represent the lightning activity over tropical Africa and South America. This is data from Schumann resonance observation. So we're talking about magnetic field, and it's an integral of lightning activity. And the red curves in both are the actual temperatures, the surface temperatures taken from an independent data set over the same region. And while the correlations aren't that great, the correlation coefficient's 0.5, 0.6, we can see that on the days where we have warmer temperatures over South America and over Africa, we generally have more lightning activity. And in the cooler periods, the cooler days, we also have a drop in the lightning activity. If we want to go further back in time and look at time series, as I mentioned, we don't really have any data going back more than a decade or two. But luckily, there are other parameters we can look at related to thunderstorms, because all the weather stations around the globe have a set amount of parameters that they measure every day when we take measurements: temperature, pressure, relative humidity. And one of them is also what we call thunder days. Now, thunder days are a day when an observer at a weather station will hear thunder, will hear the audible signal of lightning. The only problem is whether you hear one thunderbolt or if you hear 100, it's still one day. And so this is not a very exact parameter. Nevertheless, there have been a number of studies around the world looking at the long-term trends in thunder days. And here you can see from Sao Paulo in Brazil, on the top, you can actually see the thunder days from 1950s to about 2000. And we see that in the 1950s, it was maybe 60, 70 days every year where they had thunderstorms. And this has gone up to about 90 to 100 in the 2000s. So a statistically significant increase in the thunder days. And this appears also to be linked to the bottom plot, which is the temperature. The temperature changes in Sao Paulo from 1950s to 2000. About a 3.6 degree increase over a 100-year period. So this is 50 years, so half of that. And if we compare these two, we get a sensitivity that we have approximately a 10% increase in the thunder days, the number of days with thunderstorms in Sao Paulo for every 1 degree warming. Some other sites where this has been done, sorry, it's jumping around. If we look on the left here, in Alaska, now it turns out the further north we go, or south away from the equator, the more sensitive these changes appear to be. And if we look here in Alaska, from 1950s to 2010, the data is fairly scattered here. This is telling on every year how many thunder days there were, how many days of the year we had lightning. And you can see that not that many. It's, again, very high latitudes. It's mainly in the summer months. But it's gone from about 4 days in Alaska to maybe 12 days in Alaska by 2010. And although there's a lot of scatter here, this implies about a 300% change in the thunderstorm activity over the century. If we look at Southeast Asia, Southeast Australia and Japan on the right-hand side, here too we see similar trends of increases in the thunderstorm activity, both in Australia and in Japan, and all of these are statistically significant. So it does appear that there's some real changes occurring in the amount of thunderstorms, the distribution. We don't see this everywhere, but there are significant places where we... Sorry about that, just a second. Significant changes in the thunderstorm activity in different places of the world. Now, we've tried to develop a methodology of looking at thunderstorms by using some proxies. So if we don't have the thunderstorm and the lightning data, how can we actually estimate what happened in the past? And this paper we published just last year, Harrell and Price, has taken other parameters, large-scale parameters like temperature, like the humidity in the air, like the instability in the atmosphere. And we started out by looking just over Africa. And we found that if we look at the changes from the 1950s onwards, the blue curve represents the number of thunderstorms in a given pixel, a given area. The actual units are not that important. And the black curve represents the temperature over tropical Africa. And we see that both of these have been increasing with a more rapid increase since the 1990s. And we see also a link between years which are warmer with more thunderstorm activity. And so the vast majority of evidence does show that thunderstorms have been increasing in the past, in the last century. And it's fairly likely that global warming, increasing greenhouse gases, and increasing temperature are contributing to this. If we take that last plot and we actually do a scatter plot of the data points to show how temperature on the x-axis here, as it increases, is in fact impacting the number of clusters of thunderstorms, and on the right is the area of these, how big the thunderstorms are. Here we also see that the correlation coefficient of 0.7, 0.74, so a statistically significant relationship that as the temperature increases, we have an increase in thunderstorms, and on the left you can see the sensitivity. So every 1 degree warming of the surface temperatures gives us about a 40% increase in the number of thunderstorms over Africa between 1950 to 2010s. So now let's shift gear and look into the future. How do we actually estimate what may happen in the future due to the rising greenhouse gases and global warming and climate change? So for this, we need to use climate models. Climate models are basically millions of lines of code which try to simulate the Earth's climate. And we have to break down the planet into pixels or little boxes, grid boxes. And this is the first problem, because what's the best resolution? We cannot simulate things at the resolution of a meter or even a kilometer, because to do this on the whole planet, we would maybe need a few years to make one simulation. We don't have the computer power to do that yet. So we have to always reach some compromise of what's the size of our grid box. And today it's around about 1 degree, but 1 degree is still around about 100 kilometers horizontal resolution. And we know that clouds and thunderstorms occur at smaller scales than these grid boxes. And therefore we have problems with how do we actually simulate, again, thunderstorms, lightning in these climate models when the resolution is so coarse. But these models simulate everything happening from the ocean currents to the winds in the atmosphere, the production of clouds, rainfall, the interaction of sun with greenhouse gases, with aerosols, vegetation at the surface, snow cover. So these are the most complicated computer models we have today, and use the most computing power available. And these models are used then in the reports, for example, of the IPCC. The latest report of the United Nations came out just a few weeks ago, giving us what we can expect to happen in the future with our climate. So the models predict that if we're looking just at the temperature to start off with, that we have here the increase in temperatures from the 1950s until the 220s, what we've seen. Those are the observed temperatures. But we have here some forecasts based on these models into the future till the end of the century to 2100. And what happens in the future obviously depends on what we do, humanity, whether it's related to the generation of electricity, whether we use renewable energy or we stay with fossil fuels, what we do with our diets, whether we keep on eating so much beef and other crops, and what we're going to do with transportation, And many different aspects of our economies need to be addressed. And depending on what we do, we will have different outcomes of the temperature at the end of the century. If we keep on going as we're doing now, more or less, we'll have the very high emissions, and we may have a warming of maybe 4 degrees, 4.5 degrees by the end of the century globally, the global mean. In 2015, the world's countries came together to the Paris talks and Paris agreements to try to limit the warming to 2 degrees, which you can see the shaded area on the plot here. But it's not likely we'll actually meet that target. At the rate we're going now, we'll probably pass that, but we hopefully won't get to 3 or 4 degree warming. But again, these are various scenarios we have to build for the future. And depending on how warm it gets, this will have a big impact on the thunderstorms and on lightning. So how do we try to simulate this in the storm? So this is work I did nearly 30 years ago in my PhD, where we try to take these models which have this coarse spatial resolution and try to estimate how many thunderstorms can occur in a certain time, in a certain climate, location. As I mentioned, the climate models are divided up into boxes, both horizontal resolution, but also vertical. We need to have layers in the atmosphere. We also have to have layers in the ocean to try to simulate ocean currents and the flow of heat and energy in the oceans. And so with all these limitations, we need to try to estimate the cloud formation, the convective clouds, and once we have clouds, try to say something about the electrical activity. So not very simple, and we have to develop what we call parameterizations. Parameterizations are basically an assumption or simplification of the real world. And we have to say, okay, thunderstorms normally occur when we have this temperature or this humidity or this instability in the atmosphere. But we also know from observations from satellites and from radar that the height of clouds in the atmosphere, the deeper the clouds, the deeper the thunderstorms, the more lightning occurs. And so the relationship we developed was to link the flash rate F here in this equation with the height above the ground of the top of the clouds, of the convective clouds, the thunderstorm clouds. And this is based on empirical data, where the higher the clouds, the higher the thunderstorms, the more lightning activity we get. And we have a different relationship for the land and for the oceans. And we also have a relationship to separate out the intracloud to the cloud to ground by looking at the thickness of the cold section of the cloud. In other words, from the 0 degree isotherm until the top of the cloud. That's what we call the cold cloud, where we have basically ice. We may also have supercooled droplets, but when it's warmer than 0 degrees, we'll have no ice at all. And so the cold cloud is from the 0 degree temperature isotherm until the cloud top. And we found, again, empirically that the thickness of that layer is often linked to the ratio between the intracloud and cloud to ground lightning. And so we tried to put this into the NASA's climate model. And what you can see here on the right-hand side is the simulated lightning for, on the top right, June, July, August, and on the bottom, December, January, February. These are climatological seasons, so it's not for a specific year. And on the left-hand side, we have the same seasons, so June, July, August, and December, January, February, but from the model, from observations, from satellite observations, from OTD, for specific years. So we have for 1995 and 95, 96, the bottom left. So on the left, we have the observations. On the right, we have the models for the same time of year. And we would expect to see differences, but there is also lots of similarities between them. If we look at the bottom two plots, we see the central lightning over the tropical land masses over South America, Africa, Southeast Asia. And if we look on the top, we see lightning also over going up into Siberia, in Alaska, in the summer season in the northern hemisphere, with both of them showing not much lightning over the oceans. So the model does a reasonable job, but again, it's giving us some general climatology, and it's not for a specific year. And lo and behold, people have been trying to improve this ever since from this the parameterization that I developed was published in 1992, and nearly 30 years later, people are still using it. They haven't managed to improve it that much, and the improvements that have been made don't work in all models, and there are pros and cons in every method. And so I'm happy to see that this is still being used in climate models, even though it's a very simple and very coarse resolution parameterization. So what happened, if we're looking now about how thunderstorms form in the atmosphere, I'd like to give you a little bit of a lesson about the instability of the atmosphere, and that's what we need in order to have thunderstorms. Now, we call the cooling that you have in the atmosphere, when you take a balloon of air or a parcel of air and it rises up in the atmosphere, it cools because of the decrease in pressure. And it cools at a specific rate, which we call the adiabatic lapse rate or adiabatic ascent. And this adiabatic lapse rate, which is the cooling rate of air as a function of altitude due to the pressure drop, is around about 10 degrees for every kilometer. This is what we call the dry adiabatic lapse rate, because this is for air which is not saturated. And we can see that by this line here, this lambda d, the dry adiabatic lapse rate. As soon as we reach saturation, and as you cool air, eventually the air becomes saturated, and you'll have droplets forming or clouds forming in the atmosphere. Because of the release of latent heat into the surroundings, you're actually warming the air by the latent heat, and therefore the decrease in temperature with altitude is actually at a slower rate, around about 6 degrees per kilometer. And we call this the moist adiabatic lapse rate. So inside a cloud, where we have a saturated environment, we have a slower cooling with altitude than we have below the cloud. So 10 degrees per kilometer if we have an unsaturated atmosphere. And inside the cloud, it cools if we keep on pushing the air up by about 6 degrees. Now, that's the theoretical cooling rate for any air parcel which rises adiabatically. But in reality, we have a mix of many different air masses. And so in reality, we never really can measure the adiabatic lapse rate matching theory in the atmosphere. What we do measure is this red line. We call this the environmental lapse rate. And the red line can be anything, actually. But if the red line is steeper than these two black lines, implying that it's cooling at a rate faster than, say, 10 degrees per kilometer, 12 degrees per kilometer, 13, then what happens is when we take a parcel of air from the surface and it rises, it has to cool by, according to these black lines, at the rate of the 10 degrees or 6 degrees. And what we see is there's always going to be this difference in the temperature of our parcel of air compared with the environment. And the difference is always going to be positive. Our parcel of air is always going to be warmer than the environment. And if it's warmer, it's going to keep on going up. And this is what we define as an unstable atmosphere. If you measure in the atmosphere, if you send a balloon up, a radiosonde, and you measure that the lapse rate is 12 degrees per kilometer today, you know that you're going to have clouds, rain, and likely thunderstorms on that day. And so we need to always compare what we actually have, the physical, real environmental lapse rate, to these two theoretical lapse rates. So the question is, what's going to happen in the future in the warmer climate? So there are three possibilities shown by these three red lines. The first is, so let's look at the background. The black line is the dry adiabatic lapse rate. If the surface and the upper atmosphere warm at the same rate due to increasing greenhouse gases, then we get the middle line, the middle red line, where we have a warmer surface, a warmer upper atmosphere. Z is at altitude again. But if it stays parallel to the red line, sorry, to the black line, then we haven't changed the instability of the atmosphere, and we'll see no changes in the thunderstorm activity. On the other hand, if the surface warms, but the upper atmosphere warms less, then we have a steeper slope, we'll see more thunderstorms. And if we see the warming at the surface, but more warming aloft, then we'll see a stabilization of the atmosphere, and we'll have less thunderstorms. So what do the models predict? Well, the models predict, if we look on the top here first, the models predict that, and what we're seeing on the top here are predictions for 2011 to 2030, 2046 to 65, and 2080 to 2099. The x-axis are latitude from North Pole to the South Pole, 90 north to 90 south, and the y-axis is pressure or altitude. So 1,000 millibars or hectopascal at the surface, going up to the upper atmosphere, the tropopause. And the colors represent the change in temperature. If it's red, it's going to be warmer. If it's cool, it's going to get cooler. And what we see is in the tropics, close to the equator, we start to see more warming in the upper atmosphere than we're seeing at the surface. And if that's the case, then we should be getting stabilizing the atmosphere. We'll have less of a decrease in temperature as we go up. And therefore, we should maybe expect less thunderstorms in the future. However, when we run the models, for some strange reason, all the models show increases in lightning activity. You know, here, for this one model here, a 40% increase in lightning by 2100. And most of the models run show the similar sensitivity of about 10 degrees increase for every 1 degree Kelvin global warming. So this appears to be a paradox. We're seeing the atmosphere is actually becoming more stable, less likely for thunderstorms. But when we run the models into the future, we see that we actually have more lightning. So what's going on here? Well, let's take a step back and look at the climatology of lightning and rainfall from satellite data. On the top, we can see this is from the same satellite, the TRMM satellite, TRMM satellite, which had both a radar and a lightning sensor on it. And this is data for 10 years, so average from 1998 to 2007. If we look on the top of the rainfall and rank the tropical land masses according to where we have the most rainfall to where we have the least, we see that Southeast Asia, the maritime continent, has the most rainfall. It's the wettest, followed by the Amazon and followed by Africa, where Africa is the driest of these when we talk about rainfall. But when we look at lightning, Africa has the most lightning, followed by the Amazon region in the tropics and Southeast Asia. So it's going exactly in the opposite direction. And in fact, when we look over the oceans in the what we call the intertropical convergence zone, where we have the air meeting from the northern and southern hemisphere, producing a lot of rainfall over the oceans in the tropical belt, we see in the bottom not much lightning. So it turns out that lightning actually prefers drier climates. Lightning, when it gets too moist, like the monsoon rains in India, we don't have much lightning. We have in the pre-monsoon and the post-monsoon, but when we have lots of rainfall, we don't have much lightning. And so this also has to be taken into account that areas which are going to become drier maybe in the future may be more prone to lightning activity and changes. And another example I'd just like to give you is the El Nino. For those who are not familiar with El Nino, what happens in the El Nino years is that we have basically the convection, which is normally over South America, over Southeast Asia, Australia, Indonesia, where it's very wet and we have rainforests in the western part of the Pacific. In El Nino years, this convection moves over the central Pacific and even to the eastern Pacific and leaves Indonesia, northern Australia, Borneo high and dry. We have very dry conditions and droughts there and often many fires. But if we look now what happened, say, in the El Nino of 97, 98, December, January, February, the red colors show that it's very dry, very much below average rainfall, compared with the La Nina, which a year later in December, January, February, 98, 99, lots of blues, lots of rainfall. But when we look at the lightning activity, during the El Nino, which was very dry, we had 57% more lightning activity than during the wet La Nina. So again, it seems like a paradox that the drier periods are giving us more lightning activity. So if this is true, then we need to see what the models predict about rainfall into the future. And here we have a prediction from the United Nations report from for the end of the century, 2099, the percentage change in lightning. And here we have a mixed bag, because in the blue regions, And on the left, we're seeing the simulations for December, January, February. On the right for June, July, August. The blue areas, green and blue, are where we can expect in the future more rainfall. This is a rainfall map. And the brown and yellow areas show where we can have less rainfall. And the little black dots that you can see maybe on the plots here show where 90% of the models agree with each other, implying this is where we have a lot more confidence in the results. And so in the Mediterranean region, for example, we can expect maybe a 20% decrease in rainfall by the end of the century, which is already being felt in countries like Portugal, in Greece, and Italy, even here in Israel. But what does this say about lightning? Are we going to have maybe less rainfall, less thunderstorms, but maybe more intense storms? So this is what we think may happen, that we may actually have less thunderstorms in the future, but they may be a lot more intense, bringing us more lightning activity. And as I showed before, another simulation from a climate model for the end of the century, 2100, basically a 3.8 degree warming in this model. So this is a model simulation. And we can see here the increases in lightning activity, and the difference between the year 2000 and 2100 is about a 50% increase in global lightning. Not everywhere on the planet, in some places more than others, but again, the similar sensitivity of every 1 degree global warming, about a 10-degree increase in global lightning. I found this interesting plot, which shows basically the number of insurance claims for lightning-related insurance claims in the United States, and how this changes as a function of temperature. So we know that lightning is mainly in the summer months, and therefore, basically in the summer, there may be more damage and more insurance claims, but we can see here a dramatic increase in the lightning-related insurance claims in the US as the temperature goes up. And will this continue in the future? We'll have to wait and see. One factor that I haven't spoken about, we need to take into account, is aerosols. Aerosols are tiny little particles in the atmosphere, whether from sea spray or from dust or from air pollution, from factories. But we know that in the atmosphere, every single cloud drop in the atmosphere, if you see clouds outside your window, every cloud drop has a little condensation nuclei inside, what we call CCN, cloud condensation nuclei. And every ice crystal forms on an ice nuclei. And we know that low levels of these particles, low levels of CCN, like over the oceans, and on, for example, the left-hand cartoon here, when we have very low levels of CCN, of these aerosols, then there's less droplets in the cloud, but each droplet can get big and grow fairly quickly, and therefore this rain falls out fairly quickly in what we call warm rain processes, where we don't have much ice forming in these clouds, and this rain will form out fairly quickly, but will basically be the liquid process. When we have high amounts of CCN and aerosols, and this could be in polluted areas, near factories, near cities, then what happens is that there's competition between these particles for water, and so the droplets remain fairly small, and then they can be taken up above the freezing level, where they freeze and produce ice and hail. And this is the type of clouds then that we see lightning forming in. In the warm clouds, we don't see very much lightning, and that's what I showed you before with the heavy rainfall over the oceans. In the tropics, not much lightning, because this is warm rain and not cold rain process, which involves ice. And so what happens if we now add more air pollution in the future because of all of our industries and humanities' activities? Well, so we did a study to look at how smoke from biomass burning impacts lightning. And here you can see over South America, in the season where we have, it's a transition season between, say, when we have the burning and the lightning. This is man-made fires, obviously, the biomass burning related to deforestation. And on the plot, you can see what we call the aerosol optical depth. This is an index of how much pollution and particles are in the atmosphere, but it's an integral over the whole atmospheric column taken from satellite. And we also have on here the lightning taken from the Woolen lightning network. We see when the atmosphere is fairly clean, that if we do add aerosols, they actually help in producing more lightning, because we have smaller droplets, they get taken up to form ice, and then we have a lot of lightning. And by adding some of the aerosols to very clean environments, we can actually have more lightning. But if we have too much, and it's unfortunately you can't see it on this plot because this was supposed to be PowerPoint, but these points will fall down here and it will actually decrease as we cross about 0.3 aerosol optical depth. We actually get less and less lightning, and we think that this is because the storms or the atmosphere is kind of being choked by the smoke. If we look again at this lapse rate, the normal dry adiabatic lapse rate, when we have a layer of smoke, like you can see in the image here between the clouds, the smoke itself will absorb solar radiation and heat up. And therefore, we have a warm layer above the surface, which will impact this temperature profile. And therefore, the slope here will maybe be now 4 degrees per kilometer and not 6 or 10. And therefore, this addition of too much smoke will actually stabilize the atmosphere, reduce convection, and reduce the formation of thunderstorms. So a little bit of aerosols may increase lightning in the future. Too much aerosols may actually decrease it. Now, to end, I just also want to point out that lightning itself is important for climate change. We've been speaking about how climate change will impact lightning, but lightning can also feed back on the climate system, mainly through tropospheric chemistry and the production of NOx. And here we have just some field experiments flying into thunderstorms, and you can see these big spikes in nitrogen oxide, in NO concentration, which are produced in the lightning channel itself. Here we can see from Brazil, Colorado, New Mexico, that as a function of altitude, these measurements of very high concentrations of nitrogen oxide, NO, inside thunderstorms because of the production of NO from lightning. And why are we interested in NO and NOx? It's because it can basically form ozone in the atmosphere. And ozone is another greenhouse gas, traps in infrared radiation. So if we have more lightning and more NOx and more ozone, then we're going to amplify global warming. And here from modeling studies, we can see, again, this is latitude on the x-axis in each panel and altitude or pressure in the y-axis. We can see the sources of the impact of various NOx sources on the ozone concentration in the atmosphere. And here we have lightning, we have biomass burning, soils, ships, land transportation, industry, air traffic, stratospheric production, oxygen photolysis in the stratosphere. And what we see is basically that in the tropics, and especially in the southern hemisphere, we don't have too much industry, this yellow region here, we can see that basically lightning is the main source of tropospheric ozone, which is a greenhouse gas. And therefore, lightning itself can actually have a large impact on the climate. And lightning, again, occurs in thunderstorms, which are transporting large amount of droplets and hail and water vapor into the upper atmosphere. And there are various circulation patterns in the atmosphere, whether it's the Hadley circulation or the Walker circulation, which are circulating moisture and water vapor into the upper atmosphere. And so there have been a number of studies that show the link between lightning and upper tropospheric water vapor, how much water vapor we have in the upper atmosphere, the clouds in the cirrus clouds, ice crystal size, and the water vapor in the upper atmosphere also acts as an additional greenhouse gas. So if we have more thunderstorms, more lightning, more water vapor in the upper atmosphere, this again traps in more heat and can amplify global warming. And we did one study to look at this again over Africa to show, again, the lightning activity in black and the specific humidity. So this is given in grams per kilogram of grams of water vapor per kilogram of air. And we see this amazing correlation between increased thunderstorm activity and increased water vapor in the upper atmosphere. So I want to end here to leave a few minutes for questions. Basically, our climate is being changed at the moment because of increasing greenhouse gases. And our climate will drive the surface temperature around the planet, also the lapse rate, how the temperature changes as a function of altitude. We're also changing the amount of aerosols because we're changing the land surface, the forest, we're burning forests, we're changing various parameters in the climate system. And all of these three together, and maybe others, are impacting lightning and thunderstorms. the thunderstorms themselves are driving changes in the concentration of nitrogen oxides and ozone in the atmosphere, upper tropospheric water vapor, and also igniting fires, which can feed back again onto the aerosols, and the NOx and the ozone can feed back onto the surface temperature. And so we have a fairly complicated system here that by changing the climate and greenhouse gases, we can impact thunderstorms and they can feed back on the system and cause more thunderstorms in the future. So there are many questions still open. We haven't solved all the questions, and we don't know exactly how much thunderstorms will increase in each region of the world, at what rate they're going to change. But it's a fascinating area of research, and I invite many of you to join in this quest to try to understand these processes better and to get better information for the future. And I'll thank you for your time. So thank you very much.
Thank you very much, Colin, for this very interesting presentation. And we can take up a few questions if there are any. I requested you to type questions. Maybe it is you did not have time to type, so that I can take up one or two questions from the audience. If you have a question, please raise your hand, then we can unmute you. But Colin,
yes.
Colin, I have a small question. This is especially for my students and most of the other students in the field. If a student is looking forward to conduct a research on relating climate change and thunderstorms, what do you recommend him to start with? Just to clarify the question a little bit, does he need to look at the databases in the world and then develop a correlation, or what type of research theme that you are proposing to a new student coming into the field?
Good question. Well, first of all, there's lots of literature which has been written and reviews on the topic of lightning and climate. So the first thing would be to read these papers, and I can send the references to anyone who's interested, to see also the complications in this whole topic, because as I showed, temperature impacts thunderstorms, aerosols also impact it. We've now recently found that maybe land use also may have some impact through the water cycle. But if you have data, both Thunder Day data, as I showed in the beginning, which goes back some countries for more than 100 years, the Thunder Day data, and I'm sure in South Africa there's Thunder Day data as well, that would be valuable to check to see whether there are any trends in the Thunder Day data for your location going back in time. If you actually have lightning data, most networks haven't existed for more than 10, 20 years, but even that would be interesting to see if you can make a comparison between, even over 10, 20 years, the temperature data for the same location and the thunderstorm data, even on an annual basis. Were years which have been warmer in location X, did they have more thunderstorms or not? Is there any statistical link between temperature in that location and lightning? So that would be my first direction, to try to get hold of lightning or Thunder Day data and to see if there are any trends and if it can be linked to changes in temperature locally in that country or in that region. After that, there are other methods of using models, but this becomes more complicated to use either reanalysis data, which we've been using from, say, the European Center of Medium Range Weather Forecasting, ECMWF, or from NCEP in the States. It's all available for free, which gives you meteorological data based in a model format going back 50 years or so, with all the parameters you could need. And then you could take those parameters and try to also understand changes that have occurred in your local region because the data is available at, I think, 0.5 degree resolution, so 50 kilometers around the whole planet. So I think that would be the way I would start it.
Okay, thank you very much, Colin. And we have a couple of interesting questions. And the first question is quite interesting because being a Sri Lankan, living half of my life in Sri Lanka, we have observed quite opposite of what the comment says. Let me read it. In India, most of the thunder strikes happen during the monsoon. We in Sri Lanka observed it quite opposite. We have lightning during the intermonsoon period. And the question says, the monsoon happens usually when the atmospheric temperature is comparatively low. Can you please explain?
I agree with Chandima. I think for most of the research I've seen from India, the lightning is, there is lightning in the monsoon period, but less than in the pre-monsoon. And as I showed, the drier lightning prefers the drier climate. So in the monsoon, when it's very wet and it's a very type of maritime warm rain, we don't have the right conditions for electrification. So it's not only temperature. Temperature is one of the factors, but again, locally it will change. For example, here in Israel, we only have lightning activity, we only have rainfall in the winter. And so our lightning activity occurs when we have minimum temperatures here. In our summer, we have no precipitation because we're in a Mediterranean climate. So to say that everywhere we have this positive link between temperature and rainfall is obviously incorrect. We're talking on a global scale. And so in specific regions in India, this may also not be true, and they may have an opposite relation where it's actually cooler and you may have more lightning. But I'll leave that to the locals who maybe are more knowledgeable than me on the lightning in India.
Okay, thank you, Colin.
Dr. Chandima, this is Kumar. I have a slide, maybe I can show that based on the past historical data that we collected. If that's okay, I can quickly share my screen.
Is it possible? Shall we keep it for
later? Okay, we could do that later.
Later, yeah. We'll keep it for a later session because that will be interesting. And one more question from Shiromani. I guess that this is the Director General of the Department of Meteorology, Sri Lanka. Thanks for excellent presentation. What will be the lightning activity in future based on latest CMIP6 model projections?
So this all depends on how you again the parameterization you use for your lightning. If you use what we've been doing, which is basically based on cloud top height or updraft velocities, then you'll see a significant increase in the future. Similar to the CMIP models are basically a collection of these climate models used in the IPCC, and so all of the models show an increase in cloud height or convective cloud height in a warmer climate, and that's what we use to get the estimates for the lightning. Now, there has been a recent study from a British group which is using other parameters related to ice flux and in the clouds, which is also fairly uncertain. And when they use our parameterization, they also show increase in lightning, but when they use this different one, which is also somewhat related to lightning, they show a decrease in the future. But that's one group out of many, and so we need to further study this. In the CMIP6 and all those comparisons, they do not calculate lightning per se. So they don't go that extra step and say, this is what's going to happen with lightning. They only give you the parameters that you can use then to estimate lightning on your own.
Okay, thank you very much, Colin. We have a few other questions, but let me keep them to be taken after the panel discussion if we have time. So thank you again, Colin, for the wonderful presentation, and I'm sure that we are pouring with questions now. You will have some hard time during the after the panel discussion. So
no problem. And just to say that anyone who wants to contact me offline is welcome to contact me with more questions.
Okay, thank you very much. And then I'm going to the next presentation. We have another eminent figure, especially from the professional world, one of the former chairs of IEC TC81 committee, the authoritative body that develops the lightning standards for most of the countries in the world. The presentation is titled An Overview of Lightning Protection System, and it will be delivered by Mr. Michel Guthrie, and we all call him Mitch. Mitch has a background in lightning protection, which includes serving as the US Navy's technical support agent for explosive safety, where he was responsible for the development of Navy and the development of defense lightning protection and earthing standards and the applications to explosive operations. This includes representation on US national and international lightning protection standard committees, and he has been a member of NFPA Committee on Lightning Protection for over 40 years. NFPA is the main body in USA that come up with lightning protection standards as well, apart from the fire protection standards. And his career includes a tenure as a chair of NFPA committee. He has also served on other US lightning protection committees and working groups. Michel Guthrie, podium is yours, please.
Oops, it would be better if I unmute myself. Thank you, Shandima, for the introduction. Let me see now if I can share the screen.
Yeah, we can see the slides.
You see the slide set.
Mode. Yeah, okay,
Good.
Now it's perfect.
Okay, thank you. Again, thank you very much for the opportunity to present to this group today, and happy birthday to SALNet. It's a pleasure to be here. The outline for my discussion today is I want to spend some time on the historical development of lightning protection methods. And there's a reason to do that, because it's almost a full circle to where we are and what we're discussing in this group. I'll follow that with the fundamentals of lightning protection, or from that, the fundamentals of lightning protection will come out. I'm going to spend some time on international lightning protection requirements, IEC 62305. I'm going to briefly talk about parts 1, 2, and 4, because I want to spend more time on part 3, because again, that's kind of where we're going to get into the discussion later of lower cost solutions. And during that period, I'll also speak on some of the non-standard lightning protection systems that I understand, well, they're all over the world. So I'll start with Franklin's work after he learned when thunder roars, go indoors, don't fly kites. In 1752, Franklin had a proposal for a lightning protection system, and his proposed system consisted of a small iron rod of length that's about one end is 3 or 4 feet in moist ground. The other would be 6 or 8 feet above the tallest part of the building. And on the upper end of the rod, so this is one long rod, he fastens about 1 foot of brass wire, about the size of a common knitting needle. And he was keen on using a sharpened point. The reason he used the sharpened point was some of his earlier studies. He found that the sharp point was more effective in reducing the charge from a charged sphere. We've since learned that the charged sphere, the cloud, is much further away, so maybe the sharp point's not the best idea, but still not bad. His proposal was where the house is long, there may be a rod and a point at each end with a wire in the middle going from one to the other. So a very simple lightning protection system used basically only a component or two. In about 10 years, he started getting some good feedback on the effectiveness of the system. I'm giving 2 examples here. One is a report that he got where 4 houses and a vessel, a ship that was at a wharf, was struck and damaged by lightning over the last summer. That would have been 1762 or so. But your method preventing such terrible disasters is giving very convincing proof of its utility. So there was 2 different people that witnessed the event. One was the opposite house on the other side of Water Street, saw lightning diffused on the wet pavement. So what he actually saw was this not quite so good grounding system across water. So they were getting some currents about 2 to 3 meters around the foot of the conductor. Another person across the street, a few doors down, saw the lightning above. It was darting in such a direction, it appeared to hit directly over the rod. They looked at the conductor, didn't see any damage or any evidence of any event. Went to the top of the house to the rod and found that the point had been melted. Then the second event was actually a series of 9 different years of events. It's on St. Mark's Tower in Venice. It had been severely damaged by lightning, burned down a few times. As I say, over 7 different years, they've had reported of damage. In 1776, the Franklin rod was installed and he had no damage since. So from that, many other people had started installing Franklin rods and Franklin lightning protection systems. We fast forward to 1777. In this case, there was the Bureau of Ordnance in the UK had a report of a damage to a parapet wall of a 44-foot tall building. The air termination, the rod was 27 foot taller than the building, and the damage to the parapet wall was 37 feet away from the location of the rod. From that question may be, you know, is 2 rods enough, or it raised zone of protection issues. In 1823, the French Academy of Sciences released a report, a very important report at the time, Instructions sur les paratonnerres, instructions for lightning air terminations or lightning rods. It became a guide for Europe. It was published in France, but immediately interpreted into other languages, and was a European, effectively one of the first pseudo codifications of the erection of lightning conductors. in the study, these were a six-person committee of experts in electricity at the time. They proposed a cone of protection with a radius of twice the height of the air termination. So this is our first documentation of a proposed protected zone for lightning protection. In 1820 to 1847, the Royal Navy had been doing a study or did a study on warships, and observations from that questioned whether the 2-to-1 protected zone was adequate. In the report, I don't really have enough time to go into the detail, but this was a very detailed report. It suggested that 2/3 of the terminations that they had in the Royal Navy study were to the top of the mast of the ships. And then it broke down to various levels below that. So it's an interesting study, but it questioned the 2-to-1 zone. In 1880, Preece conducted some experiments measuring the electric field about a vertical air terminal. And from his studies, he concluded a 1-to-1 zone would be the more effective method. So that brings us now to a discussion or basically, what were the early standards? Effectively, the Academy of Sciences report was if one of the first. Anderson in 1879 did a more of a study, and some argue that his report, Lightning Conductors, History, Nature, and Mode of Application, was probably one of the initial lightning protection standards or the origin of lightning protection standards. Anderson picked up on, he went back to Franklin, through Preece into the Academy of Sciences report and kind of collected all of that and made some observations from that. In 1882, the Royal Meteorological Society in the UK put together what probably was one of the better studies, or maybe actually the origin of lightning protection standards, and that's their report on the lightning rod conference. So up to this point, most of the things had actually been academic studies, review of information, tests, analyses, etc. In 1904, the National Fire Protection Association in the U.S. Produced their first specifications for protection of buildings against lightning. And in this case, this is the first time that the standardization was out of the academia, and actually in this case, it was looked at from an insurance underwriting perspective. So this is people that had a vested interest. It was not only insurance underwriters, but it's also local fire marshals in both the US and Canada. So from that point of view, they were looking at actually writing a specification. The intent was a standard or specification, but it primarily adopted the 1882 conference findings and just codified them, put it in the form of a standard. So this brings us to the point of the fundamentals of lightning protection. So we see the background on a lot of information on air termination, the analysis or review of the failures, effectiveness and failures of air termination systems. Franklin's system. This is a picture of Franklin's earliest, so it shows the air termination, the down conductor, and the earthing system. So those were the three primary components or the fundamentals of lightning protection up to that point. Of course, now we also understand the importance of equal potential bonding because we have more items coming in and out of the structure. We have more metal in our structures. We've also now looked at separation distance, where we have some items that we prefer not to have a partial lightning current conducting the currents. And then we also now in the fundamentals of current lightning protection system, we had to address measures to protect against touch voltage, to protect against step potential. And we also now know that it's important that we include both maintenance and inspection to make sure the system performs in the long term the proper way, or the way intended. IEC 62305 is the initial publication, edition 1 was in 2006. 2010 is the currently published version, but we're very close to going to edition 3, and there will be some changes in that. So I'm going to speak primarily to edition 2 because that's the edition that's out now, and it was published in 2010. The first part, or it consists of 4 parts: general principles, risk management, physical damage to structures and life hazard. This is the part I'm going to spend more time on today. And then part 4, electrical and electronic systems within structures. 62305-1, the purpose of that is to provide the baseline on which all of the other parts will be discussed. It'll provide the scientific basis. It'll provide the current parameters that are used, the time functions that would be used for analyses, simulation currents used in testing, talks about loss, it talks about damage factors. These are items that are discussed primarily in part 2 in risk management, specifically in the risk assessments. And it'll also talk about lightning protection levels and lightning protection zones, where we'll give descriptions there. One of the other important parts that's lost to many is a statement in the introduction that says, there are no devices or methods capable of modifying natural weather phenomena to the extent that they can prevent lightning discharges. Some of the lightning protection, there are some air terminals that are marketed that suggest that they do otherwise. They can actually discharge the cloud or make sure the cloud doesn't hit the structure. We'll talk a little bit about the specifics later, but that's an important statement that was put in by the IEC TC81, by the technical committee, just specifically for that purpose. IEC 62305-2, I'm going to just give a couple of slides about the what it is, what it does. I don't really have time to go through a lot of the details on the assessment. We're also making a change in the 3rd edition to where we're going to be talking about frequency of damage, and that'll be a bit of a new twist on the concept. So I just, for time's sake, I'm just going to talk about the basic calculations. What the principal part of what 62305 does, the risk management document, is it provides a procedure allowing the selection of protection measures to reduce the risk below a tolerable level. The way the standard is actually developed with the parts, part 2 actually defines what protection levels, what protection measures you need to do. And then part 3 gives details on how you achieve those levels, or how you achieve those, what protection measures to use in the design and installation of the lightning protection system for direct strike, etc., for protection of people, protection of structures. It also provides information that is used in part 4 in talking about protecting electrical and electronic equipment and systems. So it's very important, and it's sort of the baseline document you use. The first thing you do is you do the assessment, and then from that you effectively have the parameters required for your design. Some countries, such as the United States, for instance, we primarily use the risk assessment method to determine the need for protection, or it's also a very good tool if I'm looking at something unique. It's really a good document for determining what the lightning risk is, and it has more purposes than simply, the first part of designing a lightning protection system. It uses a basic risk equation for the various risk parameters. It's the risk of any parameter. I'll talk about them in the next slide. The risk is the number of dangerous events per year times the probability of damage to a structure times the consequential loss. The various risk parameters that we have, it's 8 different risk parameters. It's set up to look at the source of damage, and from each of these you can determine which to go. So flashes to a structure, you have risk RA. This is a risk of danger to people, to systems, etc. Flashes near a structure is R sub M. Flashes to a line connected to a structure, or U, or V, or W, and flashes near lines connected to a structure. So it breaks it down from the type of risk and what the actual source of damage is. On 62305-4, this was one that was a little bit difficult for me to decide how do I put this information in one slide or 2 slides, because it's kind of an all-in type thing. I chose, because the purpose of this discussion today was more along the lines of talking about looking at designing lightning protection systems with lower cost alternatives. What can I do for areas that maybe don't have the ability to have a IEC 62305 type lightning protection system. So I chose not to speak too much about the protection of the equipment inside. That's something that may be a good topic for later. But one point I did want to make here is 62305 basically addresses protection against lightning electromagnetic pulses. And it's based on the lightning protection zone concept, to where you effectively have, lightning protection zone 0 is you're exposed to the full lightning environment. LPZ 0A, you would be subject to a direct strike and all the electromagnetic effects. LPZ 0B, you wouldn't be subjected to a direct strike, but you would still get all the electromagnetic effects. And then as you go inside of that, you can create zones. So like an LPZ 1, in this case, we're creating our lightning protection zone through the use of bonds at the entry points. And then we can also use, when we search protected devices where we can't do direct bonds. We can also have an area that's maybe more sensitive to electromagnetic effects, like a data center or something like that, where we want to create a different lightning protection zone. And then there would be lightning protection zone 2, and you can have up to n number of lightning protection zones, depending on the type of a structure. For IEC 62305-4, the zones are defined by the protection measures employed. So I'm doing, I'm decreasing the environment. I'm affecting the environment. So it's that's something that's related directly to the protection measures. In lightning risk assessments, and especially in the way we're going to be dealing with the edition 3, the lightning protection zone can be defined by the designer. For instance, if I'm looking at protection of people or something to that effect, I may define a zone as something to where it's a dirt floor versus a wooden floor that's isolated from the earth. So it's an area to where I'm not subjected to ground currents or step potentials, or I am subjected to step potentials. So in that case, it's used as the same term, but it's looked at a different way. And so it's, in that case, it's defined by the designer based on, I'll call it homogeneous characteristics, based on things that are common that make a difference in terms of what the lightning risk is. I just want to make that point because there has been confusion in terms of how do you define a zone, or if the zone is defined by measures employed, then there are no measures employed. How do you define in your lightning risk assessment that as a different zone? The more confusing part is you could actually have 2 different lightning protection zones in a lightning risk assessment, where one deals with the protection of the equipment and the other is dealing with protection of people, or the other effects. So just make sure, if you weren't confused before, now you got something to ask a question about.
We can't hear you, Mitch.
I think he got disconnected.
Yes, it seems. Let's wait for 1 or 2 minutes.
Yeah, otherwise we can take up some questions for Professor Price.
Yes, until I think Mr. Michel Gatry comes up, we'll take questions. And I think Dr. Tyagi was raising the hand by the time. Oh, Mitch is there. Mitch, are you there? Mitch, are you there? Yes, he's there. Mitch, we can see your slide, but not able to hear your voice. Mitch?
I think he has to unmute. He's muted somewhere.
Mitch, can you unmute yourself? Mitch, you are muted. Mitch, you are muted. As we can see, your mic is under the muted symbol. Please unmute yourself. Okay, in the meantime, let me invite Dr. Tyagi to ask your question, which I think you wanted to direct it to Prof. Colin Price.
Yeah, thank you, Professor Chandima, and really compliments to the SALNet for second anniversary, and I'm thankful for the invitation to be part of this very important presentations by Professor Colin. I got one observation as regards to the thunderstorm activity over India. You see, we have thunderstorm activities, particularly in the mainland India, during pre-monsoon and monsoon. Though the number of thunderstorm days during monsoon is higher, the severity of thunderstorms is much higher during the pre-monsoon seasons. So it has to do the severity part and the frequency. They are the two separate mechanisms which I feel needs to be considered. And it's the combination of humidity and temperature both, not alone the temperature. To say that dry areas have higher frequency of thunderstorms may not be true for all the regions. Particularly, we find that in Northwest India and adjoining parts of Central Asia, it's a dry region, and we don't have a higher frequency as compared to the Eastern India or the Southern India, which has got fairly good amount of humidity and temperature, reasonably high temperatures. So it's a combination of humidity and temperature which essentially plays a role, in my view, over the land areas. So this is my observations. Maybe it requires further refinement, so I seek guidance from Professor Colin.
Yeah, okay, thank you very much, Dr. Tyagi. I think Mitch is there, so I will keep the answering for that or commenting for that by Prof. Colin after Mitch continues his presentation. Mitch, I think you are ready now.
Yes, thank you. Sorry, I just, the computer went away. The connection and everything. Okay, so am I...
The presentation has disappeared.
Is it there now?
I think it is coming, but not yet seen. Yes, it's there.
Okay, so I'll go to full screen. My apologies. I don't know what happened on that one.
No problem, Mitch. Go ahead.
Okay, so we'll start with now. I think the problem was because I was talking about protecting electrical and electronic equipment, and I didn't spend but one slide on it, so the gods of electrical equipment took me away. All right, so IEC 62305-3, I'll spend time on specifically those components of the lightning protection system that we've talked about in the basic parameters. Types of air termination that's allowed in IEC 62305 are mast, isolated mast, isolated catenary wires. You can use rods on a structure, and you can also use mesh type lightning protection system. The positioning, they're should be located at the corners, areas that are probably most likely to be to send air
upward going streamers. Exposed points such as maybe ventilators, chimneys, anything else that's on the roof that may be exposed, and around the edges. The methods that are allowed, three primary methods. Of course, this doesn't include Faraday cage. The Faraday cage is another allowed method. The first is the protection angle method. And we'll talk about that in the next slide. And the protection angle method was the method that was discussed in the historical analyses that I gave, where we're talking about 2-to-1 and 1-to-1 zones of protection. And we'll speak in the next slide about how that's changed as we've evolved into the IEC standard. The rolling sphere method is the method that's most commonly used. It's sort of the one that's generally used by everyone, whereas some of the others may or may not be. It also has minimal limitations as to its use. And then the mesh method. In each of these three, the protective angle or the positioning is actually a function of the class of the lightning protection system. For a class 1 lightning protection system, for the rolling sphere is a 20-meter sphere, class 2, 30 meters, class 3, 45, class 4, 60-meter sphere. In the mesh size, that varies similarly. It goes from a 5x5 for a class 1 LPS to a 10x10 meter to a 15x15 meter and a 20x20 meter. For the protective angle, the graph on the right shows that instead of having just a 1 or 2 type protective angles, which still used in many standards, including US NFPA 780. But in the IEC standard, you can see that the protective angle changes based on the class of lightning protection system you're designing to, and the actual height of the structure or height of the air terminal. So you can see in this case, and this is probably one of a good graphic as to some of the understanding of why maybe the Academy of Sciences in France looked at their data and said it's a 2-to-1 angle or 2-to-1 zone, and Priest in his studies looked at it as a 1-to-1. It does vary, and if you look at the application of the rolling sphere, some of this falls right out of the rolling sphere also. So it's your protective angle is going to depend on the height of your structure and the class of the lightning protection system you're designing to. You can also use natural air terminations. In this case, what I'm showing on the right-hand side is the use of metal sheets, or you can use metal pipes for air termination systems. And this doesn't vary depending upon class of lightning protection system, but it varies by material and whether or not it's important to protect against puncture. So for the thicknesses in the middle column, these are thicknesses that will prevent puncture. These are typically 4-millimeter thick steel or titanium, 5-millimeter thick for copper, 7 for aluminum, and that's generally accepted for most air termination systems. The other thicknesses you can see here will allow burn through. So if it's okay, you don't have any flammable materials directly below, that fire may be an issue, or if you have if this is part of a roof, and you can obviously, there's a hole for rain to come through. But if that's not a problem, then these other thicknesses may be used. The next primary component is down conductors. For down conductors, it's important to provide several parallel paths. It reduces the impedance of the down conductor system. It also decreases the current density on any one conductor. So it's a very fundamental item, and it explains why we have multiple down conductors that require a multiple number of down conductors. It's also important to keep the length to a minimum. Straight path where possible. The longer it is, the greater the inductive reactance, and the greater the inductive reactance, then the higher the voltage that's going to be built up on the conductor. Equal spacing around the perimeter is suggested with ring conductors for taller structures. So the ring conductor for taller structures, these are intermediate conductors. You would have a interconnecting conductor at the earth level. That would be either the potential bonding and the bus bars or the ring earth electrodes. You should have a conductor, interconnecting conductor on the roof, so you can get all of the down conductors can participate in the current dissipation. But in some tall structures or certain structures, it's good to actually have intermediate ring conductors. So this allows shorter distances. It allows current division, and it's a much, much lower impedance system. For that same reason, you're allowed to use the steel frame of the structure. And then many countries actually encourage the use. The steel frame with the structure, I'm talking about steel I-beams. I'm not talking about, very small pieces of metal where there's a lot of overlap, the size of the overlap. So you've got very low impedance connections and very low impedance conductors, and they're generally going to be around the perimeter. It's free, it's easy to use, and it's very, very good down conductor system. For isolated lightning protection systems, only one down conductor is required to connect to the earthing. In the US, we encourage two, but only require one also. For critical installations, I would certainly recommend you provide at least two, even if I have a metal mast, provide two connections to earth, because one can be damaged and the other is current division. Current division is your friend. You get lower impedance to earth. The preferred spacing between down conductors, according to IEC 62305-3, again, that varies with the class of the lightning protection system. For classes 1 and 2, typical distance are 10 meters apart. For class 3, 15, and for class 4, 20 meters. The natural down conductors, you can use metal installations as long as the dimensions are equivalent to what's required for down conductors, and you ensure that the connectivity is durable. It's a good conductor. The metal electrically continuous reinforcing steel is allowed. In the US, we don't use this very often because there's very little quality control we can have. The construction of steel reinforced concrete structure is generally done by steel workers with no idea of what lightning protection is or what it does or how it works. They're connecting the reinforcing steel together simply to make sure when they pour the concrete that the conductor doesn't move around very much. So it's there once the concrete sets. You may or may not get good connections. For IEC systems, we allow it, but you need to confirm that the steel is continuous. There are connectors that are made specifically for this. They're approved to 62561. There are other techniques that are allowed in 62305 Part 3 also. Interconnected steel framework I've already talked about, and facade elements meeting the requirements for down conductors are allowed. I'm not a particular fan of that because it just depends on what the facade element is made of and how good a conductor it is, how significant it is. But it is allowed. Earth termination is the third primary part that we get back from Franklin's original system. Low earthing resistance, less than 10 ohms is recommended, not required, but certainly recommended. Some standards, especially in the US, call out 25 ohms. The most important part is they're all interconnected. So again, 10 ohms recommended by the IEC standard. There are two different types of earth termination systems recognized by the IEC standard. The type A system uses horizontal or vertical electrodes that are installed outside the structure. They're connected to the down conductor or to the foundation earth electrode. Most important part of a type A arrangement is it does not form a closed loop. So each individual earthing electrode is independent at the ground level. So each individual electrode may have a different resistance to earth value. Now they will be interconnected essentially back at the structure and through the structure, but you could have different resistance to earth in one part of a structure than another part of a structure if you have, like a warehouse or something like that. And a minimum of 2 earthing electrodes are required, and that's true for everything with the exception of the ring earth electrodes and the foundation electrodes, and that's because they're all one big. I mean, everything's connected to that. For type A arrangement, the minimum length it's L sub 1 for horizontal and 0.5 L1 over 2 divided by 2 for vertical. I've got a slide coming up that'll explain what that means. The minimum length for each down conductor, that's what the L minimum length is. So that's valid for each down conductor, not for the total system. And combined electrodes, you can consider the total length, again, for that down conductor, not total length for all the earthing systems. And the minimum length can be disregarded when the resistance is less than 10 ohms. So here's the slide that ties all of that back together. The vertical axis shows the L sub 1, the effective length of your electrodes, and it's plotted versus earth resistivity and versus class of lightning protection system. So for earth resistivity of 500 ohm meters, you're good for everything. It's the length is only 5 meters, and class 1 through class 4 is all the same. At that point, you start getting deviations from the different classes. For instance, let's just take an example of a Class 1 lightning protection system with a earth resistivity of 2,600, 2,800 ohm meters, and then your effective length would be 75 meters. If it was a Class 2, I'm going to use something easier here for Class 2, and we had 2,600 ohm meters, then that would only be 40, whereas for a Class 1, 40 would be required, even down to about 1,500 ohm meters. So the important part is the earth resistivity is an important factor in determining what your effective length is, depending upon your class of lightning protection system. For Type B earthing systems, again, that same graph is applicable here. This consists of a rain conductor external to the structure in contact with the soil for 80% of the length. It also consists of foundation earth electrodes forming a closed loop and a mesh network. So if I've got a ground mesh, then that'll effectively meet the requirements of a Type B earth electrode. The mean radius of the enclosed area, in this case, we're talking about a mean radius. The mean radius is determined by calculating the area of that's covered by the rain conductor or foundation earth electrode, and then get an effective radius based on that area, solving for R. So the mean radius must exceed L1. Where it's less than L1 for vertical and horizontal electrodes, you have to add a value. In this case, for vertical electrodes, it's L1 minus RE divided by 2. You need that many meters that's added to the ground, that essentially grounding point for that grounding system. For horizontal earth electrodes, it's calculated by the value of L1 taken from the graph minus R sub B that's calculated from the area of your ring earth electrode. Additional area, the electrode should be connected to the ring earth electrode where the down conductors are connected, equidistantly spaced for as many as possible. You may or may not get an equidistant spacing because that's going to depend upon where your down conductors are. But hopefully your down conductors are also equidistantly spaced. Earthing installation, Type B buried at 0.5 meter, 1 meter from external walls. Type A also buried at a depth of 0.5 meter. This is effectively issues related to step potential. You shall be able to inspect these during construction, just so something doesn't get broke before everything gets put together. And the embedded depth should also take into consideration the frost level and the freezing of the earth. So it needs to be an earth that's fairly stable. Type B is recommended for bare solid rock or areas with very little soil and for structures with extensive electronic systems or high risk of fire. Potential bonding is another one of those points in those parameters I mentioned earlier. Interconnecting means for potential bonding is bonding conductors where the continuity is not provided naturally. You can use SPDs where direct connections aren't feasible, or isolating spark gaps where the direct connections are not allowed. SPDs shall be installed where they can be inspected, and equipotential bonding should be installed at the ground level, connected through a bonding bar or a series of bonding bars. and where installation requirements are not fulfilled. Connection should be made as direct and straight as possible. Again, lower impedance. Separation distance is for the areas that I don't want current on, that I don't want to share the partial lightning currents with. So that's generally between the lightning protection system and the structure or the other items associated with the structure. And there are two approaches. I'm not going to get into that because of time, but there's a simplified approach, which is fairly easy to do. But more importantly, if you're really concerned, and especially for certain critical structures, there's a detailed approach to where you can get much more accurate detailed solutions. Simplified approach is generally going to fall on the safe side. So now we get to the non-standard lightning protection systems. These are the next three slides are those that were or items that were asked to be included, or actually 4 slides, but that's okay. This slide gives you what the IEC standards say about non-standard lightning protection systems. 62305-3 and 5.2.1 says for all types of air terminals, only the real physical dimensions of the metal air termination system shall be used for the determination of the volume protected. Any air terminals that say I have a collection area that's greater than what the rolling sphere method would provide, are not, that value is not allowed to be used as part of a lightning protection system designed to 62305. It can be used in some implementing standards. They allow those devices to be used, but not in it. For instance, they would have to be used with the same spacing as if it were a metal lightning rod. So maybe 7 meters or 5 meters, etc. Between, rather than have one device in the middle, like the Franklin rod used to do. It also says radioactive air terminals are not allowed. I don't think they're used anywhere anymore, but I wasn't sure, so I thought I'd just add that in. And the last item I talked about already when I talked about 62305-1, there are no devices or methods capable of modifying natural weather phenomena to the extent that they can prevent lightning discharges. Specifically talking about some items, dissipation arrays or charge transfer systems, I think it's been pretty well proven and documented. There should be enough literature out there that explains that the amount of charge produced by these devices really has no effect on the initiation of the step leader that's 40,000 to 50,000 feet away. The effective area of influence, if there is any, that the wind's not immediately blowing away, is unlikely to prevent other parts of the structure from producing a streamer. So if the structure is going to produce a streamer, it's probably going to produce a streamer, whether you have one of these there or not. Enhanced collection areas. There's a lot of literature on this, but given that this is a presentation to the South Asian Lightning Network, some of the best literature you've got on this was produced by Hartono. So he talked to him. There's a lot published, and send me an email or call me if you need to get any additional information from that. We've dealt with both of these or continue to deal with both of these in the U.S., so I can provide you with some information on how we've dealt with them. In terms of other non-standard, Underwriters Laboratories is ANSI UL 96 is an ANSI standard. It's basically our standard for lightning protection system components. It's our equivalent to IEC 62561. It's especially most of the, some of the parts dealing with components. In that, UL 96 will list an air terminal, and they have listed some types of enhanced collection area, the alphabet version of air terminals. And I think I'm pretty sure they list charge transfer system air terminals, but they list them as an air terminal. So the fact that they have the metal there, they satisfy the primary components of what a copper or aluminum air terminal or rod would be, and therefore they get listed that way. That listing does not mean that UL has listed that to a U.S. standard that that endorses any of the other claims. Just want to make that clear, because some may go as a marketing tool and say our air terminal is listed to UL 96. It may be, but it's not listed for any of the enhancements or any of the things that make that different from a normal air terminal, using the same spacing as you would for a normal air terminal. Lower cost solutions. This is something that we deal with quite a bit in ACLEnet, where we try to be as efficient in providing protection for as many structures as we can. And in some cases, we will meet the intent of the standard, but we may at least consider other options, especially in-country options. The important part of that, though, is the standard should always be met wherever practicable. That it's important that you meet the standard, whether that's 100% in terms of I use IEC 62561 components, or I use this thing that's actually tested to something. We will look at deviations, but any deviation should be assessed. You got to ensure that the risk of the deviation is an acceptable risk. You have to make sure that if you're using something that deviates from the standard, it meets the intent of the standard. That may mean you need to look at additional measures, like I may need to pay more attention to corrosion. Maybe I need to put a coating on this. Maybe I need to have an inspection more often than I would inspect a component that's tested and certified to IEC 62561. And you need to make sure you look at all of the applicable lightning threats. When I put that one slide up with that table, there's 8 different lightning risk factors in that. You need to look at all of them. You know, is there an issue with touch potential? Is there an issue with step potential? Is there an issue with longevity? Is there an issue with continuity? You know, do I meet all of those fundamental parts of lightning protection systems that I had in that earlier slide? And not just the 3 of the Franklin, but all of those. Do I meet all of that criteria? I need to make that analysis to make sure that when I do the deviation or I do a substitution, that the system that's there meets the intent of the IEC system. Specifically, you know, the lightning attachment point, the down conductor, the earthing system, where applicable, touch potentials, where applicable, step potentials, you know, where applicable, side flash criteria, or separation distances, equipotential bonding. So again, if local components are substituted, corrosion surveillance is probably something you need to look at. I know that sometimes using metal roofs, you make an assumption, but when you're doing some of these designs from continents away, the metal may not be the metal you think it is, and so it may corrode faster than you think. You don't get a chemical analysis on the materials that are used. So, be very careful with that, and continue to look at each of those to where you may need to change the component out, or you may need to add a down conductor or a roof conductor in an area to where you were using a natural component at one time, but maybe the natural component now is deteriorated to the point that it may not be able to perform that function. So those are very important issues. I was asked to look at some of, as part of the low cost, to look at solutions that have been made, and I picked this one because there had been a lot of discussion within this community over this example at one time. So just throwing my 2 cents in. In evaluating any solution, such as the bicycle rim example, where there's metal there, anything could be a primary attachment point for Lightening. The question is whether the air termination is capable of transferring, is capable of physically absorbing the energy, is capable of transferring that to a down conductor, and is the down conductor adequate to get that current? Does it have the conductivity to get that current to the earth with as low an impedance as possible? And is that earthing system adequate to dissipate that? And do we have provisions for touch and step potentials around it? So the questions that I would have: does the air terminal meet the material and thickness requirement? Do you have a low impedance connection to the down conductor? It doesn't look like it in this case, but I can't really maybe tell what the connection between the bicycle rim to the down conductor is. But does the down conductor meet the material and conductivity requirements? I look at this and it looks to be wood to me. And wood is definitely not a allowed material for a down conductor. And its conductivity is way too high, so you can get splintering and damage. You certainly can get currents that run down there, but that brings the other questions into play about the step and touch potential issues. And of course, I can't make any comments on the earthing system because I don't know what it is, and maybe it doesn't exist. So the main thing is looking and evaluating these are all the risk factors that are associated with these other alternative systems. Are they at an acceptable level? And if not, what do you need to do to get it to an acceptable level, regardless of what lightning protection level you choose, whether it's LPL1 or LPL2, 3, or 4. And with that, I'm using that as my summary. So thank you very much for your attention, and I'm available for questions.
Thank you very much, Mitch, for the very detailed and highly important presentation you have made. We can start with the first question. Actually, I can see a hands up, Colonel Sanjay Srivastava. The opportunity is yours. Please go ahead, unmute your mic and speak.
Good evening, Michelle, for a very, very detailed elaboration on the lightning protection system. And my question to you is that this picture which is there, which you are showing, is by me only, and it addresses the basic parameters of lightning protection system. Yes, and the safety factors have been kept in mind. Now in a country like India or a developing country or Africa, where affordability of lightning protection device is difficult at the rural level especially. So I want you, my request to you is, if you can come out with a low cost solution which can be easily adaptable, technically sound and safe. If you can suggest a solution, I'll be expecting this from you. That will be a big support to our Lightning Resilient India campaign.
It's not an easy task, but it's certainly a task that we're looking at in the ACLE net. And I think we could work with the other networks in terms of some of these solutions. Chandima and I have talked about maybe working on some solutions, and I think we could pursue that a little bit more vigorous, I guess, at this point. It's hard to say what a good solution is because the applications may be different, but I think certainly what I've seen in working with ACLE net is it started out that every school, every structure was unique. Now we're seeing there are some things that are repeatable. So it's not really unique anymore. I think as we see things, applications, and we see the solutions to the applications and how well they work or whether they need improvement, I think we'll be able to talk more about lower cost solutions. But it's something that I think I'm sure the South Asian Lightning Network, and I know the ACLE net, we're conscious of this. We understand. I mean, there's good reasons for lightning protection system components and meeting their requirements for the industrial world or those that can afford it. But many of these aren't affordable, and it's even very difficult to get them into the country sometimes just to use, even if I could afford it. So I'll accept the challenge, but don't expect an answer tomorrow.
Thank you so much for your answer. And we are here for a common goal of saving life of people, and any such suggestions which can be for larger masses are always welcome. And I am here with you in this campaign or this effort of saving life of people. Thank you so much.
Thank you.
Thank you very much, both of you. And just one word from my side. Actually, one of the biggest challenges we have at the moment is what is the criteria for developing a low-cost solution. This is actually we are now developing a paper in this regard because one thing we should not forget is that when we are developing a low-cost protection solution, we cannot compromise protection. So it's just like if you are developing a low-cost car, automobile, we cannot compromise the mobility of the vehicle. I mean, we can reduce many things, but we have to make sure that it moves. So just like another example, developing a low-cost television. So at the end of the day, if the television cannot be used to watch a movie or any channel, then the solution has no meaning. So likewise, we are now developing criteria for a way of acceptable way of reducing the cost while not compromising the protection. So once, actually, I can understand Colonel Srivastava's concerned because at the moment we really need low-cost solutions for the developing world, but at the same time we have to think about the protection. Thank you very much. And are there any other questions or comments? Then I think you can, there are several questions to Colin as well. I did not take up. So for the time being, I will now conclude the presentation by Mitch and the Q&A session. But any questions we can take up after the panel discussion as well, and during the panel discussion. At this moment, I would like to invite Dr. Sriram for a few comments to be made as the chairman of SALNet. Sriram, over to you.
Thank you so much, Professor Chandima. It's wonderful to be with all these mass today. And very nice discussions have started, and of course we are a bigger team now. What I see is South Asian Meteorological Society joining with us, and other networks like SALNet is always with us. ADPC, Asian Disaster Preparedness Center, is with us. RIMES, Regional Integrated Multi-Hazard Early Warning System, is also with us, and ALPER, Advanced Lightning and Power Energy Research, is with us. Zambian Center for Lightning Network is also with us, and French Meteorological Association or network, Meteors, is with us, and Earth Network. So we have plenty of networks and centers working together with in a common goal of saving the lives in the developing as well as developed countries. So I'm thankful to all. So let me request one of our technical person to demonstrate the recently developed SALNet's website, so that we can inaugurate on this occasion. Arka or Shubhakant, I think you are around. Can you show the demonstration version of our preliminary version of the network website?
Sure. First of all, I'd like to thank you, Professor Sharma, Professor Gomes, and esteemed speakers and all other dignitaries present here. And my heartiest congratulations to SALNet on completion of 2 years, and of course my well wishes for the future endeavor. So as Professor Sharma said, I'm sharing the screen to show you up the newly developed website of the SALNet. So let me know if all of you can see my screen here.
Yes, it is visible.
Yes. So this is the first look of the SALNet official website. And you can see there is some basic information regarding in the home page. You can see the institute from the countries belongs to are indicated here by their national flags at the top of the page. And then we can see the quick information regarding the International Lightning Safety Day. And there is a public feedback portal. If you click on this public feedback button, you can see that there is a form. So whatever your concern regarding the SALNet and other things, you can just put your comment here, and it will be come to the technical team of the SALNet, and they will duly respond to you for your concerns. Okay, and then let me back to the home page. Next is the lightning safety tips. There are some safety tips what people should do whenever they start in some places, the lightning weather is not good that much, and there is a probability of lightning there. In the next section, you can see the latest news section. This will show you up some of the latest news regarding the South Asian territories. So what are the lightning incidents happened in near past, and moreover, we can accumulate the information regarding the lightning incidents across the area, and we can gradually showing this in this panel. And in the below of that, you can see the activities area will show up all those events and the programs is being conducted by SALNet and the associate organizations. That will be shown up here as an activities. These are the mostly excerpt portion, the home page that you can see all this information. For the details, you will have other section. In About Us, you will see the SALNet, about SALNet and its mission and vision. In organization structure, you can see the basic organization structure, the executive committee of SALNet, the advisory board, and the other lightning centers. These are the member countries in the member countries. Events and research, this section is being developed. All the research and the events activities will be come up here to make the publicly demonstrate what are the events is being conducted by SALNet and what the research is being conducted by the different centers of the SALNet. And the next part, you can see the activities. These activities are the same thing that I have shown you in the home page. That was the excerpt part. And these are all of the activities, all the current activities, forthcoming activities, even the past activities will be listed here. So anybody can access this section and get information about the activities, coming activities, even the past activities from this section. The services page is comprising of all the information, all the services is being provided by the SALNet, and there is information regarding that. Anybody can visit this page and can get a clear idea regarding the services is being provided by the SALNet. And of course, the contact us will consist of the contact information and email address, how the people will contact to the SALNet authority for their any questions and any queries and request of their things. So this is the basic structure of the SALNet, the introductory structure. And I can understand then there is several scopes that it can be developed. Even some places that there is backend that can be filled up with the appropriate information. And definitely there is a scope of improvement. So anybody of you have any better idea can contact Professor Sharma. He will get to us regarding the betterment and the other ideas. Whatever you think for the good for improvement of the website. So mostly this is it, and of course I am delighted in this Foundation Day of SALNet. I got my opportunity to introduce you this new website of the SALNet, and all of you can visit this website at www.salnet.asia. So anybody can hit the www.salnet.asia. You can visit the newly introduced website of SALNet. So this is it from my part. So I'm over to Professor Sharma to continue the proceedings.
Yes, thank you so much, Shiva. Thank you for a wonderful job you have done voluntarily on for Solnet. Thank you so much, Professor Chandima. It's over to you for panel discussion and all.
Thank you very much, Dr. Sriram. And before going to the panel discussion, let me propose a vote of thanks for Dr. Sriram Sharma, the chairman of Solnet, who has done a wonderful job during the last 2 years. Actually, he volunteered to be the chairman for this period. And during the 2 periods, the center became quite quite a remarkable institute in the region, and I'm sure that the knowledge and awareness of the lightning protection, lightning safety area in the region is much more improved during this period, especially due to the exhaustive efforts of untiring efforts of Dr. Sriram Sharma. With that, may I propose, I'm sure that the members of Solnet, most of you are here. May I propose that we nominate Dr. Sriram Sharma to be the chairman for the next 2 years as well. Can someone second my proposal?
I second that, Dr. Chandima. This is Kumar.
Thank you, Kumar. Any objections? Any alternative suggestions? Mr. Gopakumar, you want to speak up?
No. I support this decision. Thank you.
Okay, thank you very much. So then I declare that Dr. Sriram Sharma will be the chairman of Solnet for the year 2022 and 2024 as well. Congratulations, Dr. Sharma, and we hope that you will continue your good efforts, and we all can collectively support you in achieving the Solnet objectives. With that, let me start the panel discussion. Today we are going to have a panel discussion regarding the future of lightning and lightning awareness in this part of the world, especially in the developing world. And we have 10 distinguished speakers. Actually, we are giving only a very short period, 3-minute period, to tell or to discuss about a certain theme for each speaker. And actually, the main idea is not to make presentations, but to have an active discussion among the panelists and as well as the participants. So we have Prof. Marianne Cooper representing ACLENET, Africa, Ms. Foster Chelsea Lubazi representing ZACLIV, the Zambian Center for Lightning, Dr. Stephanie Schmidt representing Meteorage, the French company on lightning warning, Prof. Zainal Kadir representing University Putra, Malaysia, Dr. Anirban Guha representing Tripura University, Prof. Ajit Tyagi from South Asia Meteorological Association, Mr. Man Thapa representing ADPC, Dr. KJ Ramesh representing Regional Integrated Multi-Hazard Early Warning System, Mr. Kumar Margasyami representing Earth Networks, Early Warning Systems for Severe Weather, and finally Dr. Sriram Sharma, the chairman of Solnet. We welcome all of you, and we start our short presentations with Prof. Marianne Cooper talking on power of safety education, a lesson from the USA. Marianne, over to you.
Thank you so much, Chandima. I appreciate it. And also Sriram and the other speakers here. Sri asked me to speak about the power of safety education, a lesson from the United States. So more than ACLENet, which is more Africa, I'm representing the National Lightning Safety Council from the United States. And I thank John Jensenius for his help with the slides. Well, happy birthday to Solnet. Yay! Wonderful, wonderful job, gentlemen and ladies. It's just amazing. And I can't tell you how happy it makes me. Okay, back to the US. 1998, many of the lightning experts had been speaking with the media and about all kinds of aspects of lightning, and we decided we'd get together and start and form a uniform set of recommendations. These were people that you're familiar with, people that are still active in lightning. After we came up with the recommendations for individual safety, for small groups with a short distance to evacuate, or to safety, large groups or long evacuation times like beaches, rock concerts, things like that. We also sent this out and vetted it with international people around the world. Shortly after that, in 2001, the United States Weather Service announced a send us proposals kind of thing. And so John Jensenius wrote in and said, let's do a national lightning safety campaign. We didn't have money most of these years, and all of the people were volunteers. I was one of the core members, as was Ron, Holly, and many of the other people that you know. Well, we settled on doing a National Lightning Safety Week. They had tornado weeks and hurricane weeks and tsunami weeks. And so we were doing the Lightning Week the last full week of June. That ran for 15, 16 years until NOAA decided they were not going to have any more safety weeks by themselves. Again, it was multidisciplinary. It was me as a physician, several meteorologists, physicists, engineers, safety specialists, people from NASA and NOAA who were sending off the space shots, all kinds of stuff. And we started doing lightning safety education for government meteorologists, for broadcast meteorologists on TV and radio. We sent out packets of information, and we did a lot of work with media and the general public. We had an interview team, and we've given thousands, not me, but the team has given thousands of interviews to public radio all over the world, TV programs. We've answered questions about lightning incidents. And oh, by the way, the National Lightning Safety Council here, that is the outgrowth of many of the people who retired or moved away from the NOAA Lightning Safety Week. Well, this is the number of lightning deaths from 1970 to 2020. If I draw sort of a best fit line, I don't know enough stats to do that, so this is, yes, I'll admit that. There were around 60 to 78 deaths per year back before 2000, when it leveled off in the mid 70s or so. But if I draw a line since Lightning Safety Week started, it was a little slow getting started, but now it's really rolling great. By 2018, and 2019, we were down in the low 20s. 2020, we had 17 deaths. And in 2021, so far this year, we're still in the middle of the lightning season. We still got a couple months to go, but we've had only 10 deaths. This is significant to 3 or 4 standard deviations. It's a death rate of less than 0.03 per million per year. This is where you can get lots of information. It's all free. If you can't get these down, give me a call. You got my email there. I'm happy to help anybody anywhere all over the world with lightning safety. Thank you.
Thank you very much, for the wonderful little speech, I must say. And then I would like to invite Mrs. Foster Chelsea Lubazi, the director of SUGClear. Foster, it's all yours.
I think Mrs. Foster is not available.
Okay, if Foster is not available, then the next will be Dr. Stephanie Schmidt or Stefan Schmidt.
Yes, Stefan, yeah.
Stefan, I'm sorry.
Yeah, no, I know, because the E in, okay, the pronunciation of E in English is E, but in French is E. And the difference is that Stephanie is the female name of Stefan, but no problem. So thank you very much. Thank you very much. I want to well, to express all my sympathy, and I'm very glad for to discover what you managed to do, Sriram, and all the teams, and so wow, it's wonderful. Thank you, and congratulations. Thanks to, of course, all of you attending this event. So as I have 3 minutes, I'm just going to tell a few words in my well, according to my domain of expertise, which is the thunderstorms warning systems, and just to say that informing the population in case of a thunderstorm risk means taking up 2 challenges. Well, the first is to be technically capable of informing the public with an available information in terms of thunderstorms prediction, for instance. And the second one is to make people adopting the right safety measures by knowing what to do. So today, I want to say that the first one is becoming easier and easier because there are global thunderstorms monitoring systems, for example, which allows to anticipate without necessarily the need for a country to set up a national network. And this is, for example, the case with global networks such as the GLD 360, but also Colin mentioned the woolen, and I think that in the future there will be some other global networks, and so these networks now can be used to alert anyone wherever they are in the world. So this is technically something very amazing. And technically, I would say that it's rather the capacity to broadcast the message that can be complicated. And now the possibility to warn in case of thunderstorms, as I mentioned. But here again, many countries have involved their communication systems, or in some cases, they use also systems like systems recommended by the Weather Meteorological Organization. And I mentioned, for example, the CAP protocol, Common Alerting Protocol, which allows to send messages to a large number of people. So finally, we just have to be careful not to allow the use of dangerous non-standard systems. And well, just like in lightning protection, and I think that Gopa and Shandima will not contradict me on this point, as I know their position, but also Mitch mentioned it in his presentation, to be careful with non-standard systems. But I want to say it's the same for thunderstorms warning systems. And I want to remind that this is one of the goals of a standard, the IEC 62793, dealing with thunderstorms warning systems, because if you use bad systems, it's also dangerous. So the technical aspects are not necessarily the most complex. In fact, it would be rather the human factor that is, and Marianne knows more than me that it's quite complicated, because myth, folklore, preconceived ideas, people who underestimate the danger, the ignorance of life-saving gestures. And I think this is probably this aspect that is the least obvious, which is why it is just important to enforce awareness campaigns. So sorry, I was a little bit long as usual, but thank you a lot for the organization, for inviting me, and for your attention. Thanks.
Thank you very much, Stefan. And now I would like to invite Professor Zainal Kadir from Malaysia to speak about non-conventional systems of LPS. I'm sure that it will be a critical comment from his side.
Yeah, thank you very much, Chandima, and thank you also to SALNet for this opportunity. I think lesson learned, that will be a keyword from Malaysia. I think for the past 30 years also, we have been struggle, with the non-standard lightning protection system installation in the country. And the fact that there was so many issues at that particular times, I think mainly because of lack of knowledge and then the profit-oriented sort of opportunity, from the vendors, promotion and things like that. And I think since perhaps 2000, early 2000, we have a lot of people who are pushing, towards providing a better sort of recognized lightning protection system. And I think all those struggle, finally paid off. I think in 2011, I think for the first time, through the Energy Commission of Malaysia, which is the what you call the regulator that regulates the electricity and also gas in the country. So after several sittings, meetings, discussions with various stakeholders from ministries, from the standards department, researchers, consulting engineers, and so on. So finally, the Energy Commission has issued a circular. I think that will be the first kind of document that I would say encourage for the lightning protection system installation, the recognized, which is based on the IEC 62305. And it took almost 10 years from that moment until recently, which is the 1st January 2020, where again the Energy Commission Malaysia, after the paper has been endorsed and approved by the cabinet, then it becomes mandatory to be followed. So in other words, the use of non-standard lightning protection system is totally banned in the country. And it's not just I would say banning about the usage, but also even the enforcement up to certain extent that if it can be an offense up to about 200,000 ringgit, or almost equivalent to about 50,000 USD, or you can be imprisoned for the term not exceeding 2 years if you go for the what we call the non-standard lightning protection system. So this is how serious is the government enforce and also ensure that all the buildings, whether there is ongoing building, the existing building, and the new buildings in the pipeline, so they are all actually applicable to this mandatory directive, which is also related to the Electricity Supply Act in the country. So what I can say in the quick sort of conclusion is that it is possible to do that in any other countries, provided you have a very structured in the sense that you have a regulator and you have the research, or you have through the Association of Consulting Engineer perhaps, and your Department of Standard, which all can play the roles in pushing the the actions until you reach to the extent that it came out as the directive or the policy paper. I think this is something that I'm very much happy to share, the effort that we have made through the center, as well as the role that have been played by the Energy Commission in the country until we reach to this successful, I would say, sort of policy to be enforced in the country. So I think that's all. Again, a happy birthday to Solnet. Over to you, Chandima. Thank you.
Thank you very much, Zainal, and congratulations for the for making Malaysia one of the pioneering countries in making non-standard systems rejected as a country decision. So now I'm going into Dr. Anirban Guha to talk about developing a culture of collaborative research across the region. But before giving him the mic, let me tell a word about Dr. Anirban Guha. Actually, his name was undermentioned, I think, during this event. Dr. Anirban is one of the main architects of Solnet. Actually, if it is not for him, we would not have Solnet, as he was the main organizer and the key person in organizing the International Lightning Symposium in 2019 in Tripura University, during which we have decided to form Solnet. So you are a big part of Solnet, Anirban, and thank you very much for all your support, not only by establishing Solnet, but giving a lot of support and backing up for all these uh, all these days for the couple of years passed by. Over to you, Anirban.
Thank you, Professor Chandima. It is indeed a great day for me to be present here and for giving me some opportunity for a minute to say something. As I remember, 2 years before, we are all enjoying a very good cultural program during this time. And if we can go through the videos of those programs, I could not even imagine that those will come up to this stage, because within the 2 years we have passed through the COVID-19 era, but we did not stop doing quality programs. And in fact, my center has also started doing many works that is beyond the scope of for this presentation, what we can do. Fundamentally, I'm very glad that the people from different communities are coming together from different sectors, and we are welcoming all people with open ideas. And since I belong to academics, in science it is very important to become open, at the same time critical, at the same time we have to peer reviewed everything before implementation with experimental results. Science is all about data and experiment. Even if there is a theory, if one experiment can prove it wrong, it will be wrong. So if like for non-standard lightning protection systems, I would like to say only one thing. Let us be open for peer reviewed discussion. Okay, it is not about something who is correct and who is wrong. It is very important to come to a common platform through peer review and open discussion. If it is proved after lots of experimentation, simulation, if some system is working, absolutely okay. But for that, we have to all belong to an open-minded category. If you say that I am right, that person is wrong, other person may say that I am as well right and you are wrong. So in science, this has been happening for a long time. The history shows that there has been discussion, but we should not get inside any as far as India is concerned. Yes, we really need low cost solutions. Professor Chandima mentioned that low cost solutions should not come up with a quality of the product. Okay, we have to maintain the quality with proper experimentation and proper peer review and open discussion. I am ready to accept any thing that is peer reviewed and the community accepts that way it is correct. Okay. And government of India, as far as I know, I cannot give any number here. At the state government and central government level, they are spending huge money on this. I can say that huge amount of money, but I can't name any person or I can't give any figure in this open forum. But money is available. So let us work together. We have come up to this stage in 2 years. Let us not segregate ourselves. The whole world is with us. Let us work together. Let us have technical sessions. Let us discuss. Let us present our model and let us peer review it. And I believe that we'll come up with a much better world to live. That is only my message that I give on the second birthday of the SALNet. Let us go together. Thank you very much.
Thank you very much, Dr. Anirban, for your important message. And then we pass to Prof. Ajit Tyagi, South Asia Meteorological Association is what he is representing. Over to you, Prof. Tyagi.
Thank you so much, Professor Chandima, and I'd like to compliment and congratulate Professor Sriram for successfully led SALNet for the second years of second anniversary and launching a very impressive website for the outreach. I'll endorse what Anirban has just mentioned, that we have to be open to the various issues which are related to the safety of people, to save their lives, and particularly so in the rural areas of developing countries of South Asia and Africa. Low-cost solution is there, but nobody's asking for a non-standard. We have to work for standard low-cost solutions, and I'm happy that Mitch's approach was very positive, and I'm sure technical people will take it forward. As far as SAMA is concerned, we are very happy to associate with Solnet, and we complement Solnet since when we first interacted, we did organize the SAMA organized Lightning Resilient South Asia webinar in which Professor Sriram participated, and we found that meteorological community can complement this initiative, because essentially we need to look holistically about this framework. The technical part is very important, but it's not all, and we know to achieve that 100% safety because of technical solutions is not going to happen in near future. So till then, we need to have a framework which provides end-to-end solution for saving the lives, especially in the rural areas of these countries. And for that, of course, we have got a good monitoring system now, both space-based and ground-based in South Asia. And I'm happy Dr. Ramesh will be covering. We have been now able to develop a forecasting system down from 3 to 5 days in advance about thunderstorm warnings of probable areas down to the nowcast, which the Damini's application, which is available for everyone to monitor for location specific warnings. So we have a now fairly good early warning system to take precautions, but that has to be linked with the mass awareness programs, because both at the administrative level down to the people in the rural areas, awareness about the safety measures which can be initiated even after the warning is targeted, warning is provided, is still lacking. So mass awareness programs, which all of us needs to support and extend, and many of these NGOs and the civil society communities are doing, but this needs to be strengthened. Of course, we also need to improve the end-to-end networking of various stakeholders. And as the Malaysian example is mentioned here, yes, we do need high quality standard for the critical infrastructure, but we need to have a graded specifications for different classes of safety. And the low cost, I think, solution does address to the need which is very much required, and I'm sure SALNet along with its global partners will be able to come out with such a solution which is the need of the hour. And let me assure from the meteorological community represented in the South Asian countries that will be supporting both for monitoring and early warning part of it along with the meteorological services, and also participate in the mass awareness outreach and research promotion which academic institutions wish to take up. And I really appreciate the Anirban's comments on this very issue, and let's promote the academic institutions to take up this challenging task, both for early warning and standardizing the practices in the South Asia. Thank you, and wish you a great time ahead and great future for SALNet, and we'll work together closely. Thank you.
Thank you very much, Professor Tyagi, for your very important and significant words about regional cooperation. And now I'm going to Mr. Mantapa from ADPC on ADPC incorporating PAL in the disaster preparedness. Over to you, Mr. Thapa.
Thank you, Professor Tandima, and good evening to all colleagues from Nepal. I would like to congratulate the SALNet team for celebrating second anniversary, and I wish them more successful years to come. Similarly, I would like to thank Professor Sriram Sharma and his team for organizing this wonderful event and giving opportunity for me to speak or share our experiences on protection against lightning in Nepal. As earlier speakers very clearly mentioned that globally, the number of lightning strikes has been increased dramatically. And Nepal is not an exception. Even in case of Nepal, in last 10 years, the lightning strike is growing annually. And in an average of last 10 years, we lost about 110 lives due to lightning in Nepal. Similarly, in 2017, we did a national level assessment of the ranking of disaster. And we found that lightning is coming as one of the aggressive disaster in case of Nepal after landslide. So with this brief background information, what ADPC decided to work with the several other actors, such as the Ministry of Home Affairs, academic institutions, private sector, media, and also Nepal Academy of Science and Technology to do something meaningful to reduce the impact of lightning in Nepal, especially on the death rate. We had a rounds of meeting among these major actors, including local humanitarian organizations. Then we decided to organize one-day orientation on protection against lightning. We call PAL in short in Nepal. We organized this one-day orientation in two sites, which is a regular, where lightning is a regular threat in the country. And based on the these two trainings, orientations, and then the feedback from the participants and other actors, we came back to Kathmandu. We sat together again, the same team, and we designed a 3-day training program, basically to make participants aware of what is lightning, how it strikes, and what are the basic things we can do to protect against lightning. And based on this new curricula, we designed at least 5 training program in 2019-2020 by ADPC alone. And while doing so, we also had a time to develop a very good training curricula, which is again led by Professor Sriram Sharma. And we also had developed a very good poster on protection against lightning in Nepali and circulated widely through different means and ways. Also, we had a public service announcement broadcasted almost like a month during this summer time through our local FM radio station all over the country. We developed a standard. And now with all these initiatives, what we thought is that this is not enough, because this was primarily to raise the technical capacity of Nepali professionals, largely working with the local government, central government, and academia, plus few in private sector as well. We continue our effort, and in discussion with several other actors, what we are thinking right now is to integrate the protection against lightning with broader electric fire safety, because electric fire safety is also becoming a major threat in Nepal. According to our Ministry of Home Affairs, about 80% of the total fires at home is through the electricity. So we thought that why not we also work on that one. And similarly, as ADPC is working in 26 Asian countries, and especially our program, which I'm part of it, is called Asian Preparedness Partnership. We are working in 6 countries, 3 from South Asia and 3 from East Asia, namely Nepal, Pakistan, Sri Lanka from South Asia, Cambodia, Myanmar, and Philippines from East Asia. All these 6 countries are equally prone to lightning. So what we are planning is that we are planning to organize a regional training of trainers to raise our regional capacity on protection against lightning. And I believe that this single initiative is not enough to manage all the risk generated by the lightning in this part of the world. I think we need to work together. That's how in our all training programs, discussions, and even organizing training programs, we always bring academia and private sector together. And in case of Nepal, private sector is very much interested to work with us, and they have already contributed, at least in organizing some training program. We'll continue these initiatives, but again, improving content-wise based on the need, based on the content and need of the country. And as I said, our interest is we are working together with the academic institutions. So we are trying to integrate the protection against lightning in engineering, especially electrical engineering undergrad master's program, and also in other engineering degrees. So at least the engineers who are responsible to design, implement, monitor the construction of buildings and infrastructure should be aware of the basic principle, how best we can protect our infrastructures against lightning. And then with this simple initiative, I believe that we can reduce the risk of lightning in this part of the world. I'm sure that there are so many other important actors or players who can contribute. We still need to explore that part and bring as much as potential partners to work together, not only in the academic part, but also the research publications, media, who plays a significant role in reducing disaster risk in this part of the world, another part of the world as well. This is all from my side. Thank you very much. So once again, giving this opportunity to share a little bit of our initiatives on protection against lightning in Nepal. Thank you and all the best.
Thank you very much, Mr. Thapa. And now we are going to Dr. KJ Ramesh, Regional Integrated Multi-Hazard Early Warning System. Please, the mic is yours.
Thank you very much, Dr. Gomes, and congratulations to Solnet and Dr. Sharma for taking a lot of initiatives for the region. And it is a common problem, and we have to fight. Storms. And we have now, fortunately, in India, we had very good experience of building partnership with public institutions like CROPSI. India Meteorological Department 3 years before started partnership to build an advocacy, very strong advocacy with the other stakeholders at the state level and district level disaster management authorities and the communities directly, and providing a lot of IEC material in vernacular languages. Apart from this, what on the science side, early warning capacity building enhancement part of it is 2 years before the day the science of lightning prediction became available in 2017, we introduced that prediction segment into our mesoscale models in India, and then we started producing lightning intensities and strikes, etc., at a 3-hourly interval for next 3 days, and in that has helped to identify the hottest spots of probable lightning which are going to be there in different parts of the country in 24 hours time, particularly in 3-hour time slots, and that we verified for a year in 2018, and we are very happy and operationalized that segment. And to support that, we have made our satellite image overlaid with the lightning sensor data about the frequency and intensity of the lightning as well, and with the 10 minutes, 20 minutes, 30 minutes interval on our satellite image, and then about over the radars, radar reflectivities and the satellite radar reflectivities and the lightning information were overlaid, and that gives very fine information. That update is for about 10 minutes update is there. So both these near real-time early warning information, monitoring detection information, supported by a lead time hotspot identification, where the very strong nowcast and very strong nowcast systems were built in this country, and that helped for minimizing the lives of the people to 50% in 2 years' time. So with that, what has happened is several state governments and community level institutions started working with IMD and CropC, and a lot of local level campaigns, village level campaigns, and do's and do nots were conveyed, and how to reduce the exposure in the rural areas where the deaths are comparatively higher because of lack of understanding about the safety, do's and do nots, etc. So that's where the targeted efforts are now currently going on very strongly in about 9 states in this country. A lot of experience has been gained between IMD and CropC over 2 years, and the report of CropC for IMD and CropC report of Lightning for 2020 has been uploaded in WMO website also. So that is a very, very satisfying work which India has done, and that experience we are ready to share under SALNet with all countries of South Asia, and that should help the people. Now we have lightning mapper data also available from Chinese satellite that we can overlay in addition to radar information and the local lightning information which is coming from lightning detection networks across the South Asia, which is already available by the national agencies and the earth networks put together. We have to integrate, and we have apps and already available in each country. So this knowledge sharing on live knowledge sharing of monitoring, detection and early warning segment, and we have implemented in India CAP also successfully, a common alert protocol, so that mass dissemination of lightning information can be pushed, and that CAP knowledge is available for South Asia to be built, and then SALNet will be the right kind of institution to build CAP interface for the region. And whatever knowledge we have and whatever experience we have gained between IMD and CropC through now RIMES and other institutions like SAMA and so many other partners joined in this effort, will make the campaign successful and target the minimization of the lives of the people. All the very best to the efforts of SALNet. Thank you.
Thank you very much, Dr. Ramesh, for your insightful presentation. And now we are going to Mr. Kumar Margasyami, who will be talking on supporting Asian countries with high impact of severe weather and climate change. And Mrs. Foster Lubazi, next will be you. I can see you are there now. Over to you, Mr. Kumar.
Me now? Yeah. Thank you, Dr. Chandima, and I'm glad to be here as part of SALNet. So, well, when we start off this journey back almost 8 years back, primarily our goal was to try and see how we could potentially reduce the number of deaths, not only in the Indian subcontinent, but across Asia. And so we started expanding what we call as the ENTLN, which is the Earth Network's Total Lightning Detection Network across Asia. So we have had many success in that aspect. So we started working with PAGASA, which is the National Met Agency of the Philippines. Then we implemented our lightning detection network in Cambodia, and worked with the World Bank on putting together a pilot project in Myanmar, and then expanded into Sri Lanka, set up a lightning detection network. And then, of course, India has been predominantly a major concern for us, because initially when we started off in about 2015, the yearly deaths were almost about 3,000, right, at an average every year. So we started working with several state disaster management agencies in India, which started off almost 5 years back with the state of Andhra Pradesh and then slowly expanded. right? And subsequently, we also built up relationships with academia. In fact, Dr. Anirban Guha is one of the early users of our data and has been looking at that for the northeast of India. And also we partnered with RIMES, particularly in the state of Odisha. So from that perspective, Odisha is a very interesting case study because when we started initially working with Odisha back in late 2017, I mean, they had 466 lightning deaths, and post implementation of a lightning detection network there and being able to provide early warnings to the public, in 2018, they were able to reduce deaths to 331, and in about 2019 to about 200 up to September of 2019, right? But one of the key factors that I would bring about from an early warning system perspective is one is the technology itself, right? The technology might be good, like somebody earlier pointed out, and standardized, but at the same time, there's a lot of groundwork which needs to be done. And this is where I think Odisha and the state of Karnataka also came up with certain strategies. The first was in mass awareness, being created within the public, basically posters being put at every village, every school saying what needs to be done in case of lightning, not to go under a tree or to take shelter in a safe location, right? So that was one of the biggest strategies. And I think that's very important in a country like India because a lot of the population is rural and they are the most impacted people out there, the rural people rather than the urban ones, right? At the same time, they had a mass dissemination system, which was through SMS. And of course, they had the mobile apps, right? But having said that, the most important was being able to send these early warning messages about potential lightning strikes within your area through mass SMS. For example, take the example of Karnataka, a state which is in the south of India. 2018, they had 134 lightning deaths, but they were able to, that's when we first implemented our system out there, and they were able to send out about 8.5 million SMS messages, right? But come to 2019, the deaths reduced, right, to about 34. And during that time, they were able to send out about 10.4 million SMS messages, right? So primarily what's important again is, like I mentioned, from an early warning perspective, your system could be good. Yeah, but at the same time, it's the public awareness which needs to be generated and the mass messaging of early warnings to be sent to the people, right? That is really what helps. And of course, uh, there are also our colleagues from Meteorage, which uses GLD 360, which is good, and they've been doing a lot of services within the Asian region and also Nowcast. I know Nowcast is being used in Nepal, right? So yeah, I'm using these early warning technologies. There's definitely a potential to save many more lives, And today with the ENTLN network in India, we work across 7 to 8 different states, and have been reducing deaths in each of these states, But again, the most important is educating the masses on what to do when they receive a warning message. And the second is that these warning messages have to reach the public in time. Yeah, so that's all I would like to say about, trying to save lives.
Thank you very much, Mr. Kumar. And now I would like to invite Mrs. Foster Lubazi to talk about the difficulties in promoting lightning safety awareness. I think she's the best person to talk about that, being the director of Zambian Lightning Center. Foster, over to you.
Hello, can you hear me?
Yeah, sure, very much.
Okay, and you can see me. I can switch off the video. Okay, sorry for coming in late. I completely miscalculated the time. Thank you, Shri, for that heads up. I just had to abandon what I was doing to join the meeting, but we can talk about that later. Yeah, for now, talking about the challenges in advancing lightning safety education, speaking from the Zambian experience, I think it wouldn't be far from the truth if I said for Africa, especially Black Africa, is that I think what I can say is what we are going through, what I've come to understand up to now is like, it's just, I think they're growing pains, or what would go the teething problems. I think for a long time, as we all know, I mean, Africa has mostly believed in myths, and we haven't yet really gotten to a point where we have completely broken through those myths, and I'm talking like that at all levels. I think that's why everything is so slow, because whoever you talk to, there's still some skepticism, you know, about lightning research and lightning safety. You know, it's easier in Africa or in Zambia to talk about lightning protection for equipment, electronic equipment, and maybe buildings. But when you talk about lightning protection for human beings, it's very highly believed that it's just witchcraft and all that. So that in itself is really a war. But like I said, it's teething problems, because like right now with the radio programs that we're having, we are actually hoping that in October, because we're discussing with the Zambia National Broadcasting Corporation, that they give us time to speak on lightning safety on all the local languages on radio, because of the LOSI program that we had in May, which has proved to be very effective, at least impactful. We're still discussing with the people. And I'm thinking that if we can discuss this lightning safety the whole of October in the 7 major languages in Zambia, I think it will get the whole country talking about lightning safety. And I'm hoping that that is one way we're going to start breaking through the ice of, or is it the rock of the myths that people have held on to. And I think as we discuss this, I'm sure that come the rain season, with people if people are equipped with knowledge, I hope we can see a reduction in people being struck by lightning, and hopefully we could have solved one problem. And maybe with the solving of that problem, if we can document all that, it may open other avenues and other doors for us, including to the lawmakers. Right now, we're talking with the lawmakers, but you can still see the skepticism, and also one other challenge is that in a country like Zambia, where of course the economic situation is not so good, you don't get people who can volunteer for prolonged period of times. So, like I said, like I shared on another platform, sometimes I have people with me, sometimes I'm basically alone, and understandably so, because people have to concentrate on other jobs that are giving them an income for their families. So that in itself is a challenge. It means that alone, most of the time, I can only do that much, therefore making the progress quite slow. However, the fight still continues, because it's a noble cause, and it's a necessity. It's an absolute necessity for a country like Zambia. And I'm talking to a few colleagues in the neighboring countries. I hope they can get started, but it's hard enough to just do the work in Zambia. I trust that with time, I think it's a matter of time. That's what I think. It's a matter of time, and if we can have more people come in to volunteer who will have the time and resources to volunteer to do the work with me, I think we'll do more. So I think basically for now, that's what I can say. Apart from, of course, I shouldn't forget to wish SALNet a happy anniversary. Zach there is almost 7 years. We're 6 years going into 7 years. I was thinking to myself, well, we have too many challenges that we have no time to celebrate. But I look forward to the time when we can also be able to celebrate in this manner. Thank you so much, Sri, for having me and everybody else. It's a great opportunity. Thank you so much. Back to you, Chanma.
Thank you very much, Foster, and hope that we can have similar activities in African continent as well. Now we have a very strong African continental team as well, led by Prof. Marianne Cooper and by you, Foster, yourself, and there are several others as well. So that let's think about building up to have a competition between Solnet and AcclaimNet and the African team. Actually, I'm joking. So we can have very good collaboration.
In 5 years' time.
Yes, it is the same team. Yeah, it's the same team. It's the same team that working in all these continents, and I'm really happy to see this team coming up day by day, growing by numbers. And finally, let me invite Solnet Chairman, Dr. Sriram Sharma, for an insight on Solnet objectives.
Thank you so much, Professor Chandima. Again, I have been talking and talking, although it was the day that others should talk about and discuss the problems. Anyway, it was very nice that we had good cluster and like-minded people in the single platform. Thank you so much, all the institutional leads or representatives that who accepted my invitation and joined hand today to celebrate this day. Special thanks to Professor Ajit Tyagi, Mr. Mantapa, Dr. Ramesh, and Professor Marianne Cooper, Foster Lumasi, and Professor Jainal, and Stefan, and Mr. Kumar for their presence as well as the support to the Solnet celebration. Actually, the Solnet was formed 2 years back to promote or actually mitigate the loss of lives and property damage in the region. And for that, we had an objective to raise the awareness in the region and educate the technicians as well as scientific scientists on scientific methods on lightning protection system, assist the government organizations, humanitarian organizations, and technically, particularly technically, in order to mitigate the loss of lives in the region, and work together with in collaboration with scientific institutions and research centers, and we are collaborating with different institutions in this regard, and I'm very happy to say that we have come across many events altogether, 2 physical events, international events, and 14 online events so far during these 2 years, and I'm so happy to share all these events, and during this time we are very happy that we have all this cluster of institutions together, working together with the same motive or objective. Thank you so much for being with us today, and thank you so much for proposing me as a next chairman as well for the Solnet. It's of course it's a heavy load for me, but still I think I am happy to carry it on. Thank you so much all for being with us today, and I think it's time for wrapping up. Professor Chandima, please go ahead with wrapping up.
Thank you very much, Dr. Sharma. And I think we have spent quite a lot of time, and some parts like in Malaysia, it is almost 10:40 now in the night. And so that I think rather than going to further discussion, we better wrap up the meeting now. And before that, may I ask a few things from you? One is there were several questions raised by the audience, which you can post, or which even we can direct to the Prof. Colin Price, so that he can reply you individually. And also, if there are any questions to the other panelists, please you can post them to the Solnet in the feedback form. So we will send it to the relevant people. And as one Mr. Batullah Nagraju is raising his hand, I think I will give the last chance for him to raise his comment or question. Over to you, Batullah.
Thank you so much, sir. First of all, heartily congratulations and happy SALNet Foundation, sir. Thank you for conducting this webinar, sir. Sir, actually, I have one doubt, sir. Sir, what type of solution for road transportation and sea level transportation vehicles and aviation vehicles, sir, while landing and while starting from land, what type of lightning protection solution can we expect, sir? Because these are the public places and human risk of human life also included in this one, sir. Can you please touch on this one, sir?
Okay, Batullah, I think this question needs a little longer response.
Okay.
If anyone is here, then I would like to invite to give the answer. Otherwise, there are a number of papers published in this regard. And what I can do is either send you few papers to read, and at the same time, we can you can send an email to Prof. Sriram Sharma, or even fill up the form in the Solnet web page, and we will direct it to the relevant speakers so that they will reply to you. Okay? As the time is not enough, I would like to wrap up rather than going into a detailed discussion. And this type of questions, they're very important questions. So giving a few sentence response will be little risky, so that I would like the question to be addressed properly by an expert. So thank you very much. Then with that, we'll wrap this up. And please make sure that you go through the Solnet website and make any comments with regard to our future work. And please keep in mind that this is your institute, this is your center. You can make suggestions of on what to be done. And so based on your suggestions, the team of advisors and the executive committee will decide how to proceed further and organizing future events. And before winding up, let me mention the name of Dr. Munir Ahmed from Bangladesh, who is not with us, as I can't see him today, because Munir is the one who proposed the formation of Solnet with a very friendly discussion, not officially, he came up with me and few others that why not we form an Asian center just like ACLENET, because everyone was looking at ACLENET as a role model, and he was telling that why not we have our own in the Asian region, and that's how the idea was originated. I thought that it is not fair mentioning his name at this very important moment of celebrating the second year. So thank you very much. Thanks for everyone, the participants, the speakers, panelists, and everyone. And but actually, I'm thanking on behalf of Solnet. Dr. Sri, would you like to have a last final word?
Everything is done now. I think all are tired. So thank you so much for being with us, and let's be together, work together, and work for the common goal. And we have very like-minded people together, and having the zeal to work towards the mitigation of loss of life and property damage by lightning. So I welcome everybody, and to work together in the days ahead, and I'm thankful to everyone who has contributed for making this day a wonderful day. And thank you so much, Chandima, for making this event so beautiful, beautifully organizing this, and Mr. Gopakumar, who has been technically supporting us in this regard. You are also a character of being thankful. Thank you so much, Chandima. I'm from my side, it's over.
Okay. Have a nice evening for those who are in the eastern side. Have a good day for those who are in the western side. Take care. Bye.
Thank you. Bye.
Bye. Thank you, everybody.
Thank you all. Bye.
Thank you, folks. Appreciate it. Bye.